The Big Bang Theory is a scientific explanation for the origin of the universe. It suggests that the universe began as a singular, incredibly hot and dense point approximately 13.8 billion years ago. This theory is supported by a wealth of observational evidence and is widely accepted by the scientific community. The term Big Bang was actually coined by British astronomer Fred Hoyle during a radio broadcast in 1949. Interestingly, Hoyle intended it as a somewhat dismissive term, as he was a proponent of the steady-state theory, which posited that the universe had no beginning or end and was in a constant state of creation. Despite his intentions, the name stuck and became the popular term for this cosmological model. The concept of the Big Bang Theory can be traced back to the early 20th century. In 1912, American astronomer Vesto Melvin Slipher observed that galaxies were moving away from the Earth, which was later confirmed by Edwin Hubble in the 1920s. Hubble's observations led to the formulation of Hubble's law, which states that the universe is expanding. This was a groundbreaking discovery because it implied that the universe was once much smaller and denser than it is today. The idea of an expanding universe was further supported by the discovery of cosmic microwave background radiation, CMB, in 1965 by Arnold Penzias and Robert Wilson. This faint glow of radiation is considered the afterglow of the Big Bang, a remnant from the early universe that provides a snapshot of the universe when it was just 380,000 years old. The uniformity and spectrum of the CMB match predictions made by the Big Bang model, providing strong evidence for its validity. But what exactly happened during the Big Bang? According to the theory, the universe began in a state of singularity where all matter and energy were concentrated in an infinitely small point. This singularity then underwent rapid expansion, a process known as cosmic inflation, which occurred within the first fraction of a second after the Big Bang. During this period, the universe expanded exponentially, smoothing out any initial irregularities and setting the stage for the formation of galaxies and other large-scale structures. As the universe continued to expand and cool, it went through several key phases. In the first few minutes, nuclear fusion occurred, leading to the formation of light elements such as hydrogen and helium in a process known as Big Bang nucleosynthesis. This period lasted for about 3 minutes and resulted in the creation of the primordial elements that would later form stars and galaxies. Following nucleosynthesis, the universe entered a period known as the Dark Ages, which lasted for several 100 million years. During this time, the universe was filled with neutral hydrogen gas, and there were no stars or galaxies to illuminate the cosmos. It wasn't until the first stars and galaxies formed that the universe began to light up, marking the end of the Dark Ages and the beginning of the era of reionization. The Big Bang Theory also provides explanations for several other observed phenomena. For instance, it accounts for the abundance of light elements in the universe, the large-scale structure of the cosmos, and the isotropy and homogeneity observed in the cosmic microwave background radiation. These observations are consistent with the predictions made by the Big Bang model, further solidifying its status as the leading explanation for the origin and evolution of the universe. Despite its success, the Big Bang Theory is not without its challenges and unanswered questions. One such question is the nature of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. While the Big Bang Theory provides a framework for understanding the universe's expansion, it does not fully explain the properties or origins of these mysterious components. Another area of ongoing research is the concept of cosmic inflation. While inflationary theory explains many observed features of the universe, such as its large-scale uniformity, the exact mechanism driving inflation remains unknown. Scientists continue to investigate potential models and seek observational evidence to support or refute these ideas. The Big Bang Theory also raises philosophical and existential questions about the nature of the universe and our place within it. If the universe had a beginning, what, if anything, existed before the Big Bang? Is our universe just one of many in a multiverse, each with its own set of physical laws and constants? These questions remain the subject of intense debate and exploration, both within the scientific community and beyond. In conclusion, the Big Bang Theory is a cornerstone of modern cosmology, providing a comprehensive explanation for the origin and evolution of the universe. It is supported by a wide range of observational evidence and has withstood numerous tests and challenges over the decades. However, like all scientific theories, it is subject to revision and refinement as new data and insights emerge. As we continue to explore the cosmos and deepen our understanding of the universe, the Big Bang Theory will undoubtedly remain a central focus of scientific inquiry and discovery. We explored the monumental event known as the Big Bang, the cosmic explosion that occurred approximately 13.8 billion years ago, marking the origin of our universe. This event set the stage for everything we know today, from the formation of galaxies to the emergence of life on Earth. It was a moment of unimaginable energy and density, where all matter and energy were concentrated in a singular point before expanding rapidly. This expansion laid the groundwork for the universe's current structure and composition. Expanding horizons, we delve into the ongoing story of our universe's expansion. This act focuses on the fascinating and somewhat mysterious phenomenon of the universe's continuous growth. But what exactly does it mean for the universe to expand? And what role does dark energy play in this process? To understand the expansion of the universe, we must first consider the observations made by astronomers in the early 20th century. Edwin Hubble, an American astronomer, made a groundbreaking discovery in the 1920s. He observed that distant galaxies were moving away from us, and the farther away a galaxy was, the faster it seemed to be receding. This observation led to the formulation of Hubble's law, which states that the velocity at which a galaxy moves away is proportional to its distance from us. This was the first direct evidence that the universe is expanding. But what drives this expansion? Enter the concept of dark energy. Dark energy is a mysterious and invisible force that permeates all of space and is believed to be responsible for the accelerated expansion of the universe. It is a form of energy that counteracts the force of gravity, causing galaxies to move apart at an ever-increasing rate. Despite its significant influence on the universe's expansion, dark energy remains one of the most enigmatic components of the cosmos. It is estimated to make up about 68% of the universe, yet its true nature is still largely unknown. The discovery of dark energy came in the late 1990s when two independent teams of astronomers were studying distant supernovae, which are exploding stars. They found that these supernovae were dimmer than expected, suggesting that the universe's expansion was not slowing down, as previously thought, but was instead accelerating. This was a surprising and revolutionary finding that challenged our understanding of the cosmos. So, what are the implications of an expanding universe driven by dark energy? For one, it means that the universe is not static, but is dynamic and ever-changing. As the universe expands, galaxies move farther apart, and the space between them increases. This expansion affects the large-scale structure of the universe and has profound implications for its ultimate fate. One of the key questions that arise from this expansion is, what will happen to the universe in the distant future? There are several theories about the universe's ultimate fate, each dependent on the properties of dark energy and the overall density of the universe. One possibility is the Big Freeze, where the universe continues to expand indefinitely, becoming colder and more dilute as galaxies drift apart and stars burn out. Another possibility is the Big Rip, where the expansion accelerates to the point that galaxies, stars, and even atoms are torn apart. The concept of an expanding universe also raises questions about the nature of space and time. If the universe is expanding, does that mean space itself is stretching? And how does this expansion affect our understanding of time? These are complex questions that scientists continue to explore as they seek to unravel the mysteries of the cosmos. In addition to dark energy, the expansion of the universe is also influenced by dark matter, another mysterious component of the universe. Unlike dark energy, Dark matter does not drive the expansion, but instead exerts a gravitational pull that helps hold galaxies and galaxy clusters together. It is thought to make up about 27% of the universe, yet, like dark energy, its true nature remains elusive. As we continue to explore the expanding universe, new technologies and observations are providing us with unprecedented insights. Telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are allowing us to peer deeper into the cosmos, observing galaxies and phenomena that were previously beyond our reach. These observations are helping scientists refine their models of the universe's expansion and gain a better understanding of dark energy and dark matter. Expanding Horizons takes us on a journey through the ongoing expansion of the universe and the mysterious forces that drive it. The discovery of dark energy has revolutionized our understanding of the cosmos, revealing a universe that is dynamic and ever-changing. As we continue to explore these expanding horizons, we are reminded of the vastness and complexity of the universe and the many mysteries that remain to be uncovered. What new discoveries await us as we delve deeper into the cosmos? How will our understanding of dark energy and dark matter evolve in the coming years? These are the questions that drive the field of cosmology and inspire us to continue exploring the universe's expanding horizons. Stellar Nurseries, we delve into the fascinating process of star formation, a pivotal phenomenon in the universe that takes place within massive cosmic clouds composed of gas and dust. These regions, often referred to as stellar nurseries, are the birthplaces of stars, where the raw materials of the cosmos come together under the influence of gravity to ignite nuclear fusion and give rise to new stars. The story of star formation begins in these interstellar clouds, also known as molecular clouds due to their composition primarily of molecular hydrogen. These clouds are vast, sometimes spanning hundreds of light years across, and are the densest parts of the interstellar medium. They contain not only hydrogen, but also helium and trace amounts of heavier elements and molecules, including dust particles. The presence of dust is crucial as it plays a significant role in cooling the gas, allowing it to collapse under its own gravity. But how exactly does a star form from these seemingly chaotic clouds? The process starts with the cloud's gravitational instability. Over time, regions within the cloud become denser and begin to collapse under their own gravity. This collapse is often triggered by external forces such as shock waves from nearby supernovae, collisions between clouds, or the influence of spiral arms in galaxies. These forces compress the gas and dust, increasing the density and initiating the collapse. As the cloud collapses, it fragments into smaller clumps, each of which can potentially form a star. These fragments, known as protostellar cores, continue to collapse and heat up due to the conversion of gravitational energy into thermal energy. The core's temperature and pressure rise until nuclear fusion ignites in the core, marking the birth of a new star. This process can take millions of years, and during this time, the protostar is often surrounded by a rotating disk of gas and dust, from which planets and other celestial bodies may eventually form. One of the most intriguing aspects of stellar nurseries is the diversity of stars they produce. The mass of the protostellar core largely determines the type of star that will form. Low-mass cores give rise to smaller, cooler stars like red dwarfs, while more massive cores can form larger, hotter stars, such as blue giants. The most massive stars, although rarer, have significant impacts on their surroundings due to their intense radiation and powerful stellar winds, which can disrupt the surrounding cloud and influence the formation of other stars. Stellar nurseries are not only fascinating for their role in star formation, but also for the rich tapestry of phenomena they exhibit. These regions are often sites of intense activity, with jets and outflows from young stars, complex magnetic fields, and interactions between stars and their environment. Observations of stellar nurseries, particularly in different wavelengths such as infrared and radio, provide valuable insights into the early stages of star formation and the conditions within these cosmic cradles. The study of stellar nurseries also raises intriguing questions about the formation of planetary systems. As stars form, The surrounding disks of gas and dust can coalesce to form planets, moons, asteroids, and comets. Understanding the processes within stellar nurseries helps astronomers piece together the story of how our own solar system, and others like it, came into existence. Moreover, stellar nurseries are not isolated phenomena. They are part of the larger cycle of matter in the galaxy. Stars formed in these nurseries will eventually evolve and die, returning material to the interstellar medium through processes such as supernovae or stellar winds. This material enriches the galaxy with heavier elements, which are then incorporated into new generations of stars and planets, continuing the cycle of cosmic evolution. Stellar Nurseries explores the captivating process of star formation within the universe's vast molecular clouds. These stellar nurseries are the cradles of stars, where gravity, gas, and dust come together to ignite nuclear fusion and create the diverse array of stars we observe in the night sky. Through the study of these regions, we gain a deeper understanding of the universe's life cycle and the origins of the celestial bodies that populate it. As we continue to explore these cosmic nurseries, we uncover more about the intricate processes that shape the universe and our place within it. What new discoveries await us in the depths of these stellar nurseries? How do the conditions within these regions influence the formation of stars and planets? The journey into the heart of stellar nurseries promises to reveal even more about the mysteries of the cosmos. In the previous act, Stellar Nurseries, we explored the fascinating process of star formation within massive cosmic clouds of gas and dust. These regions, known as stellar nurseries, are the birthplaces of stars, where the delicate balance of gravity and pressure leads to the creation of new celestial bodies. As we transition from the birth of stars, we now delve into a more enigmatic and captivating subject in black hole mysteries. Black holes are among the most intriguing and mysterious phenomena in the universe. They are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This characteristic makes black holes invisible, detectable only through their interaction with surrounding matter and the effects they have on nearby objects. But what exactly is a black hole? At its core, a black hole is formed when a massive star exhausts its nuclear fuel and collapses under its own gravity. This collapse results in a singularity, a point of infinite density, where the laws of physics as we know them break down. Surrounding this singularity is the event horizon, the boundary beyond which nothing can escape the black hole's gravitational grip. One of the most intriguing aspects of black holes is their ability to warp space-time itself. According to Einstein's theory of general relativity, massive objects like black holes cause a curvature in the fabric of space-time. This curvature affects the path of light and the motion of objects, leading to phenomena such as gravitational lensing, where light from distant stars is bent around a black hole, creating distorted or multiple images of the same star. Black holes come in different sizes, ranging from stellar mass black holes, which are formed from the remnants of massive stars, to supermassive black holes that reside at the centers of galaxies, including our own Milky Way. These supermassive black holes can have masses equivalent to millions or even billions of suns. But how did these colossal entities form? Are they the result of merging smaller black holes, or do they grow by accreting vast amounts of matter over time? Another fascinating question is what happens to matter that falls into a black hole. As matter approaches the event horizon, it is subjected to intense gravitational forces, causing it to heat up and emit radiation. This process, known as accretion, can produce powerful jets of energy that are observable across vast distances. However, once matter crosses the event horizon, it is lost to the universe, its information seemingly erased from existence. This leads to the famous information paradox, a puzzle that challenges our understanding of quantum mechanics and general relativity. The study of black holes is not just theoretical. Astronomers have observed the effects of black holes on their surroundings, providing indirect evidence of their existence. For instance, the detection of gravitational waves, ripples in space-time caused by the collision of massive objects like black holes, has opened a new window into the universe, allowing scientists to study these enigmatic entities in unprecedented detail. Despite these advances, many questions remain unanswered. What lies beyond the event horizon? Is there a way to retrieve information that falls into a black hole? Could black holes be gateways to other universes, as some theories suggest? These mysteries continue to captivate scientists and the public alike, driving ongoing research and exploration. As we continue our journey through the cosmos, the study of black holes offers a glimpse into the fundamental nature of the universe. Their enigmatic presence challenges our understanding of physics and inspires us to push the boundaries of knowledge. What new discoveries await us in the depths of these cosmic enigmas? The answers may reshape our understanding of the universe and our place within it. We delved into the enigmatic nature of black holes, those fascinating space-time anomalies that possess such a strong gravitational pull that not even light can escape from them. We explored how these cosmic phenomena form, typically from the remnants of massive stars that have ended their life cycles in supernova explosions. As the core of such a star collapses under its own gravity, it can form a black hole, a region of space where the gravitational pull is so intense that it warps the fabric of space-time itself. We also examined the different types of black holes, from stellar mass black holes, which are formed from individual stars, to supermassive black holes, which reside at the centers of galaxies and contain millions to billions of times the mass of our sun. These supermassive black holes are thought to play a crucial role in the formation and evolution of galaxies, influencing the motion of stars and gas within them. Moreover, we discussed the concept of the event horizon, the boundary surrounding a black hole beyond which nothing can return. This led us to ponder the mysteries that lie beyond this point of no return, where the laws of physics as we know them cease to apply. We also touched upon the idea of singularity, the core of a black hole where density becomes infinite and the known laws of physics break down. We shift our focus from the mysterious depths of black holes to the grand cosmic ballet of galaxies. Our attention turns to the Milky Way, the galaxy that is home to our solar system, and its inevitable collision course with the Andromeda Galaxy, our closest galactic neighbor. The Milky Way and Andromeda are both spiral galaxies, characterized by their flat, rotating disks of stars, gas, and dust, with a central bulge and spiral arms extending outward. These galaxies are part of the Local Group, a collection of more than 50 galaxies bound together by gravity. The Local Group itself is part of the larger Virgo supercluster, which contains thousands of galaxies. The impending collision between the Milky Way and Andromeda is a cosmic event that has been set in motion by the gravitational forces at play within the Local Group. But how do we know that this collision is going to happen? Astronomers have been able to measure the motion of Andromeda relative to the Milky Way using the Doppler effect, which reveals that Andromeda is moving towards us at a speed of about 110 kilometers per second, 68 miles per second. This measurement, combined with our understanding of the gravitational dynamics within the Local Group, indicates that the two galaxies are on a collision course. But what will happen when these two massive galaxies collide? Will it be a catastrophic event that spells doom for the stars and planets within them? Interestingly, the vast distances between stars mean that direct collisions between stars are unlikely. Instead, the gravitational interactions between the two galaxies will cause them to merge over the course of several billion years, resulting in a new, larger galaxy. During the collision, the structure of both galaxies will be dramatically altered. The spiral arms of both the Milky Way and Andromeda will be disrupted, and their central supermassive black holes may eventually merge as well. This merger will likely trigger a burst of star formation as clouds of gas and dust are compressed and heated by the gravitational forces at play. The final result of this cosmic dance will be a new elliptical galaxy, sometimes referred to as Milkomeda or Milkdromeda. This new galaxy will be different in structure from the spiral galaxies that merged to form it, with a more rounded, three-dimensional shape. While this galactic collision may sound dramatic, It's important to note that it will unfold over a timescale of billions of years, far longer than the human lifespan. In fact, the collision is not expected to begin for another 4 billion years, and the complete merger will take several billion years more to finalize. As we contemplate this grand cosmic event, we are reminded of the dynamic and ever-changing nature of the universe. Galaxies are not static entities. They are constantly interacting, merging, and evolving over time. The collision between the Milky Way and Andromeda is just one example of the many galactic interactions that have shaped the universe as we see it today. So what does this mean for our solar system? While the collision will certainly alter the structure of the Milky Way, it is unlikely to have a direct impact on our solar system. The vast distances between stars mean that our sun and its planets are unlikely to collide with any other stars. However, the gravitational forces at play during the merger could potentially alter the orbit of our solar system within the new galaxy. In conclusion, the impending collision between the Milky Way and Andromeda is a fascinating example of the dynamic nature of the universe. It serves as a reminder of the immense scales of time and space that govern cosmic events, and it invites us to ponder the future of our galaxy and our place within it. As we continue to study the universe and its many mysteries, we gain a deeper appreciation for the intricate dance of galaxies and the forces that shape them. What other cosmic events await us in the future, and how will they continue to shape the universe we call home? We explored the fascinating and inevitable cosmic dance between the Milky Way and the Andromeda Galaxy. This event, predicted to occur in about 4.5 billion years, is a spectacular example of the dynamic and ever-changing nature of our universe. The gravitational forces at play will lead to a merging of these two massive galaxies, resulting in a new galaxy formation. This cosmic event is a reminder of the vast scales of time and space that govern the universe and the intricate gravitational interactions that shape the cosmos. We turn our attention to a fundamental aspect of our universe's history: the cosmic microwave background, CMB. This is the afterglow of the Big Bang, a faint cosmic radiation that fills the universe and provides us with a snapshot of the universe when it was just 380,000 years old. But what exactly is the cosmic microwave background, and why is it so important to our understanding of the universe? The cosmic microwave background is essentially the leftover radiation from the Big Bang, the massive explosion that marked the beginning of the universe approximately 13.8 billion years ago. In the moments following the Big Bang, the universe was incredibly hot and dense, filled with a plasma of particles and radiation. As the universe expanded, it cooled down, allowing protons and electrons to combine and form neutral hydrogen atoms. This process, known as recombination, occurred about 380,000 years after the Big Bang. Before recombination, the universe was opaque because the free electrons scattered photons, preventing light from traveling freely. However, once neutral atoms formed, photons could travel unimpeded, and the universe became transparent. The light from this era is what we now observe as the cosmic microwave background. It is a relic of the early universe, providing a direct glimpse into its conditions at that time. The CMB is remarkably uniform, with a temperature of about 2.7 Kelvin, just above absolute zero. However, it is not perfectly uniform. Tiny fluctuations in temperature and density, known as anisotropies, are present. These anisotropies are crucial because they represent the seeds of all future structure in the universe, including galaxies, stars, and planets. By studying these fluctuations, scientists can learn about the conditions of the early universe and the processes that led to the formation of large-scale structures. The discovery of the cosmic microwave background was a pivotal moment in cosmology. In 1965, Arnold Penzias and Robert Wilson, two radio astronomers, accidentally discovered the CMB while working at Bell Labs. They detected a persistent noise in their radio antenna that could not be attributed to any known source. This noise turned out to be the cosmic microwave background, confirming the Big Bang Theory and earning them the Nobel Prize in Physics in 1978. Since its discovery, the CMB has been studied extensively through various missions and experiments. One of the most significant missions was the Cosmic Background Explorer, COBE, launched by NASA in 1989. COBE provided the first detailed measurements of the CMB's temperature fluctuations, confirming the predictions of the Big Bang Theory and providing insights into the early universe's conditions. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, provided even more precise measurements of the CMB. WAAP's data allowed scientists to determine the universe's age, composition, and geometry with unprecedented accuracy. It revealed that the universe is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy, a mysterious force driving the accelerated expansion of the universe. More recently, the Planck satellite, launched by the European Space Agency in 2009, has provided the most detailed map of the CMB to date. Planck's observations have refined our understanding of the universe's age and composition, confirming and expanding upon the findings of previous missions. The study of the cosmic microwave background continues to be a vital area of research in cosmology. It serves as a powerful tool for testing theories about the universe's origin, composition, and evolution. By analyzing the CMB, scientists can probe the fundamental physics of the early universe, including the nature of inflation, a rapid expansion that occurred in the first moments after the Big Bang. Inflation theory suggests that the universe underwent a brief but exponential expansion, smoothing out any irregularities and setting the stage for the large-scale structure we observe today. The CMB provides indirect evidence for inflation, as the patterns of temperature fluctuations align with predictions made by inflationary models. Moreover, the CMB is a window into the mysterious realm of dark matter and dark energy. While dark matter does not emit or absorb light, its gravitational effects influence the distribution of matter in the universe, leaving imprints on the CMB. Similarly, dark energy, responsible for the universe's accelerated expansion, affects the CMB's temperature fluctuations. As technology advances, future missions and experiments will continue to refine our understanding of the cosmic microwave background and its implications for cosmology. Scientists are developing new techniques to measure the polarization of the CMB, which can provide additional insights into the early universe's conditions and the nature of inflation. In conclusion, the cosmic microwave background is a cornerstone of modern cosmology, offering a glimpse into the universe's infancy and the processes that shaped its evolution. It is a testament to the power of scientific inquiry and the ability of human ingenuity to unravel the mysteries of the cosmos. As we continue to study the CMB, we are reminded of the profound questions that remain unanswered and the exciting discoveries that await us in the exploration of our universe's origins. What new insights will future observations of the CMB reveal? How will they reshape our understanding of the universe and our place within it? The journey of discovery continues, guided by the faint, ancient light of the cosmic microwave background. In the previous act, we delved into the cosmic microwave background, the faint glow that fills the universe and serves as a remnant from the Big Bang. This TMB is crucial for understanding the early universe, as it provides a snapshot of the universe when it was just 380,000 years old. It is essentially the afterglow of the Big Bang, a form of electromagnetic radiation that fills the universe and can be detected in every direction. The CMB is a key piece of evidence for the Big Bang Theory, as it supports the idea that the universe was once in a hot, dense state and has been expanding ever since. The uniformity and slight fluctuations in the CMB also give us insights into the distribution of matter in the early universe, leading to the formation of galaxies and large-scale structures. We turn our attention to another enigmatic component of our universe, dark matter. Unlike the CMB, dark matter does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. But what exactly is dark matter, and why is it so important? Dark matter is a form of matter that does not interact with electromagnetic forces, meaning it does not emit, absorb, or reflect light, making it invisible and detectable only through its gravitational effects. It is called dark because it does not emit any radiation that we can detect, and matter because it has mass and exerts gravitational force. Despite being invisible, dark matter plays a crucial role in the universe. It is believed to make up about 27% of the universe's total mass and energy content, far outweighing the ordinary matter, such as stars, planets, and galaxies, that makes up only about 5%. The existence of dark matter was first proposed in the 1930s by Swiss astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, Zwicky noticed that the galaxies were moving much faster than expected based on the visible mass of the cluster. He concluded that there must be some unseen mass providing the additional gravitational pull needed to hold the cluster together. This unseen mass was later termed dark matter. Further evidence for dark matter came from the study of galaxy rotation curves. In the 1970s, astronomer Vera Rubin observed that stars in the outer regions of spiral galaxies were orbiting at much higher speeds than expected based on the visible mass of the galaxies. According to Newton's laws of motion and gravitation, the orbital speed of stars should decrease with distance from the galactic center, similar to how planets in our solar system orbit the sun. However, Rubin found that the rotation curves of galaxies were flat, indicating the presence of additional unseen mass extending far beyond the visible edge of the galaxies. Dark matter also plays a crucial role in the formation and evolution of galaxies. In the early universe, dark matter clumped together under the influence of gravity, forming the gravitational scaffolding around which ordinary matter could accumulate and form galaxies. Without dark matter, the universe as we know it would not exist. Galaxies would not have formed, and the large-scale structure of the universe would be vastly different. But what is dark matter made of? Despite its significant presence in the universe, the exact nature of dark matter remains one of the biggest mysteries in astrophysics. Several candidates have been proposed, including weakly interacting massive particles, WIMPs, actions, and stereo neutrinos. WIMPs are hypothetical particles that interact only through the weak nuclear force and gravity, making them difficult to detect. Actions are another hypothetical particle that could account for dark matter, and they are predicted to have very low mass and interact very weakly with other particles. Stereo neutrinos are a type of neutrino that do not interact via the standard weak nuclear force, making them a potential dark matter candidate. Scientists are actively searching for dark matter through various experiments and observations. Direct detection experiments aim to observe dark matter particles interacting with ordinary matter in highly sensitive detectors located deep underground to shield them from cosmic rays and other background radiation. Indirect detection experiments look for the products of dark matter annihilations or decays, such as gamma rays or neutrinos, using telescopes and detectors in space and on Earth. Collider experiments, such as those conducted at the Large Hadron Collider, LHC, search for evidence of dark matter particles being produced in high-energy particle collisions. Despite these efforts, dark matter has yet to be directly detected, and its true nature remains elusive. However, its gravitational effects are undeniable, and it continues to be a fundamental component of our understanding of the universe. The search for dark matter is not just about understanding an invisible component of the universe. It is also about uncovering new physics beyond the standard model of particle physics and gaining deeper insights into the fundamental nature of matter and the universe itself. As we continue to explore the cosmos, the shadow of dark matter looms large, challenging our understanding and pushing the boundaries of science. What new discoveries await us in the quest to uncover the secrets of dark matter? Will we finally be able to detect these elusive particles and unravel the mysteries of the universe? The search for dark matter is a journey into the unknown, and it holds the promise of transforming our understanding of the cosmos. We delve into the fascinating world of neutron stars, the incredibly dense remnants left behind after massive stars explode in supernovae. These stellar remnants are among the most extreme and enigmatic objects in the universe, offering a glimpse into the fundamental forces and particles that govern the cosmos. Neutron stars are born from the catastrophic death of a massive star. When a star with a mass greater than about 8 times that of our Sun exhausts its nuclear fuel, it can no longer support itself against the relentless pull of gravity. The core of the star collapses under its own weight, causing a supernova explosion that ejects the outer layers into space. What remains is a neutron star, a compact object with a mass between 1.4 and 2.16 solar masses, but with a radius of only about 10 kilometers. Imagine compressing the mass of the Sun into a sphere the size of a city. That's the incredible density of a neutron star. The name neutron star comes from the fact that these objects are primarily composed of neutrons, subatomic particles with no electric charge. During the collapse of the star's core, protons and electrons are crushed together to form neutrons, resulting in a star that is essentially a giant atomic nucleus. The density of a neutron star is so immense that a sugar cube-sized amount of its material would weigh about as much as all of humanity combined. Neutron stars exhibit a range of fascinating phenomena due to their extreme properties. One of the most intriguing is their rapid rotation. As the core of the star collapses, it spins faster, much like a figure skater pulling in their arms to spin faster. This conservation of angular momentum can result in neutron stars rotating hundreds of times per second. These rapidly spinning neutron stars are known as pulsars, named for the pulses of radiation they emit as they rotate. Pulsars were first discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, and their regular pulses were initially thought to be signals from extraterrestrial civilizations. The magnetic fields of neutron stars are also incredibly strong, often billions of times stronger than Earth's magnetic field. This intense magnetism can accelerate particles to near-light speeds, producing beams of radiation that sweep across the sky as the star rotates. When these beams are aligned with Earth, we detect them as regular pulses, hence the name pulsar. Neutron stars are not only fascinating on their own, but also play a crucial role in our understanding of the universe. They serve as natural laboratories for studying the behavior of matter under extreme conditions that cannot be replicated on Earth. The study of neutron stars can provide insights into the fundamental forces of nature, such as the strong nuclear force that holds atomic nuclei together. Moreover, neutron stars are key players in some of the most dramatic cosmic events. When 2 neutron stars orbit each other in a binary system, they gradually lose energy through gravitational radiation, causing them to spiral closer together. Eventually, they merge in a cataclysmic collision, producing gravitational waves, ripples in the fabric of space-time that were first directly detected by the LIGO Observatory in 2015. These mergers also create heavy elements like gold and platinum, enriching the universe with these precious materials. The study of neutron stars is a rapidly evolving field, with new discoveries and insights emerging regularly. For instance, the recent detection of fast radio bursts, FRBs, mysterious and powerful bursts of radio waves from distant galaxies, has sparked interest in the potential role of neutron stars in their origin. Could these enigmatic signals be linked to the extreme environments around neutron stars? As we continue to explore the universe, neutron stars remain a key focus of astronomical research. Their extreme properties challenge our understanding of physics and push the boundaries of what we know about the cosmos. What secrets do these dense remnants hold, and what can they teach us about the nature of matter and the universe itself? We invite you to join us on a journey into the heart of these extraordinary objects. Discover the forces that shape them, the phenomena they produce, and the questions they raise. As we unravel the mysteries of neutron stars, we gain a deeper appreciation for the complexity and wonder of the universe. What new discoveries await us in the dance of the neutron star ballet? In the previous act, Neutron Star Ballet, we explored the fascinating world of neutron stars. These are the incredibly dense remnants left behind after massive stars explode in supernovae. Neutron stars are composed almost entirely of neutrons, the neutral particles found in atomic nuclei. Despite their small size, typically about 20 kilometers in diameter, they can contain more mass than our sun. This density is so extreme that a sugar cube-sized amount of neutron star material would weigh about as much as all of humanity combined. The act delved into the physics that govern these celestial objects, including their intense gravitational fields and rapid rotation, which can lead to phenomena such as pulsars, neutron stars that emit beams of radiation detectable from Earth. We shift our focus from the cosmic scale to the microscopic, exploring the bizarre behavior of matter at the smallest scales. The quantum realm is the domain of quantum mechanics, a fundamental theory in physics that describes nature at the smallest scales of energy levels of atoms and subatomic particles. But what makes the quantum realm so peculiar, and why does it defy our everyday experiences? At the heart of quantum mechanics is the concept of wave-particle duality. This principle suggests that every particle or quantum entity can be described as both a particle and a wave. For instance, light can behave as a wave, which explains phenomena like interference and diffraction, but it can also behave as a particle, which is evident in the photoelectric effect, where light knocks electrons off a material. This duality is not just limited to light. Electrons and other particles exhibit similar behavior. Another key feature of the quantum realm is the uncertainty principle, introduced by Werner Heisenberg. This principle states that certain pairs of physical properties, like position and momentum, cannot both be known to arbitrary precision. The more accurately we know one, the less accurately we can know the other. This is not due to limitations in measurement, but rather a fundamental property of quantum systems. How does this principle affect the way we understand the universe? Quantum entanglement is another fascinating aspect of quantum mechanics. When two particles become entangled, the state of one particle instantly influences the state of the other, no matter how far apart they are. This phenomenon puzzled even Albert Einstein, who famously referred to it as spooky action at a distance. Entanglement has profound implications for our understanding of reality and has practical applications in emerging technologies like quantum computing and quantum cryptography. The quantum realm also introduces the concept of superposition, where particles can exist in multiple states at once until they are observed. This is famously illustrated by the thought experiment known as Schrödinger's cat, where a cat in a sealed box is simultaneously alive and dead until someone opens the box and observes it. Superposition is a cornerstone of quantum computing, where qubits can represent both 0 and 1 simultaneously, allowing for complex computations that classical computers cannot perform efficiently. Quantum tunneling is another phenomenon that defies classical intuition. It describes the ability of particles to pass through energy barriers that they seemingly shouldn't be able to surmount. This process is crucial in many natural and technological processes, such as nuclear fusion in stars and the operation of tunnel diodes in electronics. The quantum realm challenges our classical understanding of reality, prompting us to rethink concepts like determinism and locality. While classical physics is deterministic, meaning that future states of a system can be predicted with certainty given its current state, quantum mechanics introduces an element of probability. Instead of definite outcomes, quantum mechanics provides probabilities for different outcomes, leading to a fundamentally probabilistic view of the universe. As we delve deeper into the quantum realm, we encounter the concept of quantum fields, which underpin the standard model of particle physics. This model describes the fundamental particles and forces that constitute the universe, except for gravity. Quantum field theory combines quantum mechanics with special relativity and provides a framework for understanding how particles interact and transform. The quantum realm is not just a theoretical playground. It has practical implications and applications that are transforming technology and science. Quantum mechanics is the foundation of modern electronics, enabling the development of transistors, lasers, and semiconductors. It also plays a crucial role in the development of new technologies, such as quantum computing, which promises to revolutionize fields like cryptography, optimization, and materials science. As we continue to explore the quantum realm, we are faced with profound questions about the nature of reality, the limits of human knowledge, and the potential for new technological breakthroughs. How will our understanding of the quantum realm evolve in the future? What new discoveries await us as we probe deeper into the mysteries of the universe at its most fundamental level? The quantum realm challenges us to expand our horizons and embrace the strange and wondrous possibilities that lie beyond the limits of classical physics. We delve into the fascinating life cycle of our sun and its profound influence on the solar system. The sun, a massive ball of hot plasma, is the central star of our solar system and plays a crucial role in sustaining life on Earth. But have you ever wondered how the sun came to be and what its future holds? Let's explore the life cycle of the sun and its impact on the solar system. The sun, like all stars, was born from a cloud of gas and dust known as a nebula. This process began around 4.6 billion years ago. Gravity caused the nebula to collapse, and as it did, the material at the center began to heat up, eventually forming a protostar. This protostar continued to gather mass from the surrounding nebula until it reached a high enough temperature and pressure in its core to ignite nuclear fusion. This marked the birth of our sun, a main sequence star. During the main sequence phase, the sun fuses hydrogen into helium in its core, releasing energy in the form of light and heat. This process is what powers the sun and provides the energy necessary for life on Earth. The sun has been in this stable phase for about 4.5 billion years and is expected to remain so for another 5 billion years. But what happens when the sun runs out of hydrogen fuel? As the sun exhausts its hydrogen supply, it will enter the next phase of its life cycle, the red giant phase. During this phase, the core will contract and heat up, causing the outer layers to expand. The sun will grow so large that it will engulf the inner planets, including Mercury and Venus, and possibly even Earth. This expansion will cause the sun to cool and redden, hence the name red giant. Eventually, the core will become hot enough to start fusing helium into heavier elements like carbon and oxygen. This process will continue until the core runs out of helium. At this point, the sun will shed its outer layers, creating a beautiful shell of gas and dust known as a planetary nebula. The core that remains will become a white dwarf, a small, dense remnant of the sun. Over billions of years, this white dwarf will cool and fade away. The life cycle of the sun has a significant impact on the solar system. During its main sequence phase, the sun's energy drives the climate and weather on Earth, supports photosynthesis in plants, and influences the orbits of the planets. The sun's magnetic field also extends throughout the solar system, creating the heliosphere, which protects the planets from cosmic radiation. As the sun enters the red giant phase, its increased luminosity and size will have dramatic effects on the solar system. The intense heat and radiation will strip away the atmospheres of the inner planets, and the habitable zone, the region where conditions are right for liquid water to exist, will move outward. This could potentially make the outer planets, like Mars or the moons of Jupiter and Saturn, more hospitable to life. The eventual formation of a planetary nebula will enrich the interstellar medium with heavy elements, contributing to the formation of new stars and planets. This cycle of stellar birth, death, and rebirth is a fundamental process in the universe, driving the evolution of galaxies and the creation of new solar systems. The sun's influence extends beyond its physical effects. It has shaped the development of life on Earth and has been a source of inspiration and wonder for humans throughout history. From ancient civilizations that worship the sun as a deity to modern scientists who study its behavior and predict its future, the sun has always been a central figure in our understanding of the cosmos. As we continue to explore the solar system and beyond, understanding the life cycle of the sun and its influence on the solar system is crucial. It helps us appreciate the delicate balance that allows life to thrive on Earth and provides insights into the potential for life elsewhere in the universe. In conclusion, the sun's life cycle is a symphony of cosmic events that shapes the solar system and influences the conditions necessary for life. From its birth in a nebula to its eventual transformation into a white dwarf, the sun's journey is a testament to the dynamic nature of the universe. As we look to the future, the study of the sun and its life cycle will continue to be a vital part of our quest to understand our place in the cosmos. What new discoveries await us as we explore this solar symphony? Only time will tell. We delve into the fascinating and complex world of theoretical physics, specifically focusing on the concept of cosmic strings. These are hypothetical one-dimensional topological defects which are believed to exist in the fabric of spacetime. But what exactly does this mean? And why is it significant in the realm of physics and cosmology? To begin with, let's break down the term cosmic strings. The word cosmic refers to the universe or cosmos, indicating that these strings are universal in nature. The term strings suggests that these are long, thin, and possibly infinitely extended objects. Unlike the strings we encountered in everyday life, cosmic strings are not made of matter, but are instead defects in spacetime itself. Imagine a tiny, incredibly dense line stretching across the universe, thinner than an atom, but with immense mass and energy. The concept of cosmic strings arises from the field of theoretical physics, particularly in the study of the early universe and the forces that shaped it. They are thought to have formed during phase transitions in the early universe, similar to the way cracks form in ice as water freezes. These phase transitions occurred as the universe cooled and expanded, leading to the formation of different forces and particles that we observe today. Cosmic strings are predicted by certain models of grand unified theories, GUTs, which aim to unify the fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. According to these theories, cosmic strings could have formed when the universe was just a fraction of a second old, during a period known as the Grand Unification Epoch. During this time, the universe underwent rapid expansion and cooling, leading to the breaking of symmetries and the formation of defects like cosmic strings. One of the most intriguing aspects of cosmic strings is their potential impact on the structure of the universe. Due to their immense mass and energy, cosmic strings would have a strong gravitational pull, capable of bending light and affecting the motion of galaxies. This gravitational influence could lead to observable phenomena, such as gravitational lensing, where the light from distant objects is bent around the string, creating multiple images or distorted views of the object. Moreover, cosmic strings could play a role in the formation of large-scale structures in the universe. As the universe expanded, cosmic strings could have acted as seeds for the formation of galaxies and galaxy clusters, providing the gravitational pull needed to draw matter together. This idea is particularly appealing to cosmologists, as it offers a potential explanation for the distribution of galaxies and the large-scale structure of the universe. Despite their theoretical significance, cosmic strings have not yet been observed directly. Detecting cosmic strings is a challenging task, as they are incredibly thin and would not emit light or other forms of radiation. Instead, scientists rely on indirect methods to search for evidence of cosmic strings, such as looking for gravitational lensing effects or searching for specific patterns in the cosmic microwave background radiation, the afterglow of the Big Bang. The study of cosmic strings also intersects with other areas of theoretical physics, such as string theory and quantum gravity. In string theory, the fundamental building blocks of the universe are not point particles but tiny, vibrating strings. While cosmic strings and the strings of string theory are conceptually different, both ideas challenge our understanding of spacetime and the nature of the universe. Furthermore, cosmic strings could provide insights into the nature of dark matter and dark energy, two of the most mysterious components of the universe. Dark matter is an invisible form of matter that makes up about 27% of the universe's mass, while dark energy is a mysterious force driving the accelerated expansion of the universe. Understanding cosmic strings could shed light on these enigmatic phenomena and help answer fundamental questions about the universe's composition and evolution. In conclusion, cosmic strings are a captivating and complex topic in theoretical physics, offering potential insights into the early universe, the formation of cosmic structures, and the fundamental forces of nature. While they remain hypothetical, the search for cosmic strings continues to inspire physicists and cosmologists, driving them to explore the deepest mysteries of the universe. As research progresses, who knows what new discoveries and insights cosmic strings might reveal? Could they hold the key to unifying the forces of nature or unlocking the secrets of dark matter and dark energy? The quest to understand cosmic strings is a testament to humanity's enduring curiosity and desire to comprehend the cosmos. We delved into the fascinating concept of cosmic strings, which are theoretical one-dimensional defects in the fabric of space-time. These cosmic strings are hypothesized to be incredibly thin, yet immensely dense, with the potential to stretch across the universe. They are remnants from the early universe, possibly formed during phase transitions in the universe's infancy. The idea is that these cosmic strings could warp spacetime around them, creating gravitational effects that might be detectable. This concept, while theoretical, opens up intriguing possibilities for understanding the universe's structure and the forces at play within it. We turn our attention to the multiverse theory, a concept that pushes the boundaries of our understanding even further. The multiverse theory suggests that our universe might not be the only one. Instead, there could be multiple universes existing parallel to ours, each with its own distinct properties and laws of physics. This idea challenges the traditional view of a singular universe and invites us to consider a much larger and more complex reality. The multiverse theory arises from several different scientific theories and observations. One of the most prominent is the theory of cosmic inflation. According to this theory, the universe underwent a rapid expansion shortly after the Big Bang. This inflation could have caused different regions of space to become isolated from each other, effectively creating separate universes. Each of these universes could have different physical constants and laws, leading to a vast diversity of possible realities. Another source of the multiverse theory is the interpretation of quantum mechanics known as the many-worlds interpretation. In quantum mechanics, particles exist in a state of probability until they are observed, at which point they choose a specific state. The many-worlds interpretation suggests that instead of a single outcome occurring, all possible outcomes happen, each in its own separate universe. This means that every decision, every quantum event could spawn a new universe, leading to an infinite number of parallel realities. String theory also contributes to the multiverse theory. String theory posits that the fundamental particles of the universe are not point-like dots, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, giving rise to the various particles we observe. String theory requires additional dimensions beyond the familiar 3 dimensions of space and 1 of time. These extra dimensions could allow for the existence of multiple universes, each with its own unique configuration of dimensions and physical laws. The concept of a multiverse raises many intriguing questions. If there are multiple universes, how do they interact, if at all? Could we ever detect or travel to another universe? What would these other universes be like? Would they be similar to ours, or would they be completely alien with different forms of matter and energy? One of the challenges of the multiverse theory is that it is difficult to test or observe directly. Our current scientific instruments and methods are designed to study our own universe, and detecting other universes would require new approaches and technologies. However, some scientists believe that indirect evidence for the multiverse might be found in the cosmic microwave background radiation, the afterglow of the Big Bang. Anomalies or patterns in this radiation could hint at interactions with other universes. The multiverse theory also has philosophical implications. It challenges our understanding of reality and our place within it. If there are countless universes, each with its own version of events, what does that mean for concepts like fate, free will, and identity? Are there versions of ourselves living different lives in other universes? How do we define what is real when there are potentially infinite realities? Despite the challenges and uncertainties, the multiverse theory continues to captivate the imaginations of scientists and the public alike. It represents a bold step in our quest to understand the nature of existence and the true scope of the cosmos. As we continue to explore the universe and develop new theories and technologies, who knows what we might discover about the multiverse and our place within it. In conclusion, the multiverse theory is a fascinating and complex idea that expands our understanding of the universe and challenges our perceptions of reality. It invites us to consider the possibility of multiple universes existing parallel to ours, each with its own unique properties and laws. While the theory is difficult to test and observe directly, it offers a tantalizing glimpse into a much larger and more intricate cosmos. As we continue to explore and learn, the multiverse theory remains a compelling area of scientific inquiry and philosophical reflection. What do you think lies beyond our universe? Could there be other worlds, other lives waiting to be discovered? The possibilities are as vast as the multiverse itself. We delved into the fascinating concept of the multiverse theory, which proposes the existence of multiple universes running parallel to our own. This idea challenges our understanding of reality and suggests that there might be countless other versions of our universe, each with its own unique laws of physics and possibilities. The multiverse theory opens up a realm of endless possibilities, where every decision and event could lead to a different universe. It raises intriguing questions about the nature of existence and whether our universe is just one of many in a vast cosmic landscape. We shift our focus to another groundbreaking concept in the realm of physics: gravitational waves. These are ripples in space-time, caused by some of the most violent and energetic processes in the universe. But what exactly are gravitational waves, and why are they so significant? Gravitational waves were first predicted by Albert Einstein in 1916 as part of his general theory of relativity. According to this theory, massive objects like stars and black holes warp the fabric of space-time around them. When these massive objects accelerate, such as when two black holes orbit each other and eventually collide, they can create ripples in space-time that propagate outward at the speed of light. These ripples are what we call gravitational waves. Imagine space-time as a vast, invisible fabric stretched across the universe. When a massive object moves, it disturbs this fabric, creating waves that travel through space. These waves carry information about their origins and the nature of gravity itself. But why are gravitational waves important, and what can they tell us about the universe? The detection of gravitational waves opens up a new way of observing the universe. Unlike light or other electromagnetic waves, gravitational waves can pass through matter without being absorbed or scattered. This means they can carry information from regions of the universe that are otherwise inaccessible to us, such as the interiors of black holes or the very early universe moments after the Big Bang. The first direct detection of gravitational waves was made by the LIGO Laser Interferometer Gravitational Wave Observatory collaboration in 2015. This historic event confirmed Einstein's century-old prediction and marked the beginning of a new era in astrophysics. The detected waves were generated by the merger of two black holes, each about 30 times the mass of the Sun, located about 1.3 billion light-years away. This collision released more energy in the form of gravitational waves than the combined light of all the stars in the observable universe at that moment. But how do scientists detect these elusive waves? LIGO and similar observatories use incredibly sensitive instruments to measure the minute distortions in space-time caused by passing gravitational waves. These instruments consist of long arms arranged in an L shape, with laser beams bouncing back and forth between mirrors at the ends of the arms. When a gravitational wave passes through, it slightly changes the length of the arms, and this change is detected by the interference pattern of the laser beams. The precision required for this measurement is astounding. LIGO can detect changes in length smaller than 1,000th of the diameter of a proton. The discovery of gravitational waves has profound implications for our understanding of the universe. It provides a new tool for probing the cosmos, allowing scientists to study phenomena that were previously beyond our reach. For instance, gravitational waves can help us learn more about the nature of black holes, neutron stars, and other exotic objects. They can also provide insights into the fundamental nature of gravity and the structure of spacetime itself. Moreover, gravitational waves offer a unique way to test the predictions of general relativity in extreme conditions. By comparing the observed properties of gravitational waves with theoretical predictions, scientists can test the limits of Einstein's theory and search for potential deviations that might point to new physics. As we continue to explore the universe through the lens of gravitational waves, we may uncover answers to some of the most profound questions in science. What happens when black holes collide? How do neutron stars merge? And what do these events tell us about the fundamental forces of nature? Could gravitational waves reveal new insights about the early universe and the conditions that led to the formation of galaxies and stars? The study of gravitational waves is still in its infancy, and there is much more to learn. As technology advances and new observatories come online, we can expect to detect more gravitational wave events and gather more data. This will help us build a more complete picture of the universe and our place within it. In conclusion, gravitational waves represent a revolutionary tool for exploring the universe. They provide a new way to observe cosmic events and deepen our understanding of the fundamental laws of physics. As we continue to study these ripples in spacetime, we may uncover new mysteries and expand our knowledge of the cosmos. What other secrets does the universe hold, waiting to be revealed through the study of gravitational waves? The journey of discovery is just beginning, and the possibilities are as vast as the universe itself. In the previous act, we delved into the fascinating concept of gravitational waves, which are essentially ripples in spacetime. These waves are generated by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. Gravitational waves were first predicted by Albert Einstein in 1916 as part of his general theory of relativity. But it wasn't until 2015 that they were directly detected by the LIGO Observatory. This groundbreaking discovery opened up a new way of observing the universe, allowing scientists to listen to the cosmos in addition to observing it with telescopes. We turn our attention to the captivating process of planetary formation. How do planets like Earth, Mars, or Jupiter come into existence from mere cosmic dust and debris? This act will unravel the mysteries behind the birth of worlds, a process that takes place over millions of years and involves a series of complex and fascinating stages. The story of planetary formation begins in vast clouds of gas and dust in space, known as molecular clouds. These clouds are primarily composed of hydrogen molecules, along with helium and trace amounts of other elements. Within these clouds, regions of higher density can form due to gravitational forces, leading to the creation of a protostar. But how does this relate to the formation of planets? As the protostar forms, it is surrounded by a rotating disk of gas and dust, called a protoplanetary disk. This disk is the birthplace of planets. The material within the disk begins to collide and stick together, forming small particles known as planetesimals. These planetesimals are the building blocks of planets. Over time, they collide and merge, growing larger and larger through a process known as accretion. But what determines whether a planet becomes a rocky world like Earth or a gas giant like Jupiter? The answer lies in the location within the protoplanetary disk. Closer to the star, where temperatures are higher, rocky planets tend to form because the heat prevents volatile compounds like water and methane from condensing into solid ice. Further out in the disk, where it is cooler, gas giants can form as ices and gases are able to accumulate. As planetesimals grow into protoplanets, their gravitational pull increases, allowing them to attract more material. This process continues until the protoplanet becomes a fully fledged planet. However, the journey is not always smooth. Collisions between protoplanets can lead to dramatic events, sometimes resulting in the formation of moons or even the complete destruction of a protoplanet. One of the most intriguing aspects of planetary formation is the role of migration. Planets do not always stay in the same place where they formed. They can migrate inward or outward within the protoplanetary disk due to interactions with the disk material or other planets. This migration can have significant effects on the architecture of a planetary system, influencing the final arrangement of planets. The study of exoplanets, or planets outside our solar system, has provided valuable insights into planetary formation. Observations of distant planetary systems have revealed a wide variety of planet types and arrangements, challenging our understanding of how planets form and evolve. For example, the discovery of hot Jupiters, gas giants that orbit very close to their stars, suggests that planetary migration is a common and important process. As we explore the process of planetary formation, we must also consider the role of time. The formation of a planet is not a quick event. It takes millions of years for a planet to form and evolve into a stable world. This long timescale means that we cannot directly observe the entire process, but must instead piece together clues from observations of young stars and their protoplanetary disks, as well as from computer simulations. The study of meteorites and the composition of planets in our own solar system also provide important clues about planetary formation. Meteorites, which are remnants of the early solar system, contain information about the conditions and processes that were present during the time of planet formation. By analyzing these ancient rocks, scientists can gain insights into the materials and processes that led to the formation of planets. In conclusion, the formation of planets is a complex and dynamic process that involves the interplay of gravity, collisions, and migration within a protoplanetary disk. From the initial dust and gas in a molecular cloud to the diverse worlds we observe today, the journey of planetary formation is a testament to the incredible forces and processes at work in the universe. As we continue to study this fascinating process, we are not only learning about the origins of our own solar system, but also gaining a deeper understanding of the countless other worlds that populate the cosmos. What new discoveries await us as we continue to explore the universe? How will our understanding of planetary formation evolve with future observations and technological advancements? The story of planetary formation is far from over, and it promises to be an exciting journey of discovery and exploration. We explored the fascinating process of planetary formation. We delved into how planets are born from the cosmic dust and debris that orbit stars. This process begins in the vast, swirling clouds of gas and dust known as molecular clouds. Within these clouds, regions of higher density begin to collapse under their own gravity, forming what are known as protostars. As these protostars evolve, the surrounding material forms a rotating disk where particles collide and stick together, gradually building up into planetesimals. Over time, these planetesimals coalesce to form full-fledged planets. This intricate dance of cosmic materials gives rise to the diverse array of planets we observe in the universe today. Now, we turn our attention to an equally captivating and far more explosive phenomenon: gamma-ray bursts. These are the most powerful explosions known in the universe, releasing more energy in a few seconds than our sun will emit over its entire 10 billion-year lifetime. But what exactly are gamma-ray bursts, and what causes these colossal cosmic events? Gamma-ray bursts are intense flashes of gamma rays, which are the highest energy form of electromagnetic radiation. They were first discovered in the late 1960s by the Vela satellites, which were launched by the United States to monitor compliance with the Nuclear Test Ban Treaty. These satellites detected unexpected bursts of gamma rays coming from space, leading to the discovery of GRBs. There are two primary types of gamma-ray bursts: long-duration and short-duration bursts. Long-duration GRBs last more than 2 seconds and are thought to be associated with the collapse of massive stars. When a massive star exhausts its nuclear fuel, its core collapses into a black hole or neutron star, while the outer layers are expelled in a supernova explosion. This process can generate a long-duration GRB, accompanied by a supernova known as a hypernova. Short-duration GRBs, on the other hand, last less than 2 seconds and are believed to result from the merger of two compact objects, such as neutron stars or a neutron star and a black hole. These mergers create gravitational waves and result in the formation of a black hole, accompanied by a short but intense burst of gamma rays. One of the most intriguing aspects of gamma ray bursts is their afterglow. After the initial burst of gamma rays, they emit radiation across the electromagnetic spectrum, from X-rays to visible light and radio waves. This afterglow can last for days, weeks, or even longer, providing astronomers with valuable information about the environment surrounding the burst and the mechanisms driving these powerful explosions. Gamma ray bursts are not only fascinating in their own right, but also serve as important tools for astronomers. Because they are so bright, GRBs can be observed from great distances, allowing scientists to study the early universe. Some GRBs have been detected from as far back as when the universe was less than 1 billion years old, providing insights into the formation of the first stars and galaxies. The study of gamma ray bursts also intersects with other areas of astrophysics, such as the search for gravitational waves. The merger events that produce short-duration GRBs are also sources of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity. The simultaneous detection of a GRB and gravitational waves from the same event would provide a wealth of information about the physics of these cataclysmic occurrences. Despite the progress made in understanding gamma ray bursts, many questions remain. What are the precise mechanisms that produce the intense gamma ray emission? How do the properties of the progenitor stars or merging objects influence the characteristics of the burst? And what role do magnetic fields play in shaping these explosions? As we continue to observe and study gamma ray bursts with increasingly sophisticated telescopes and instruments, we are likely to uncover more about these enigmatic events. The exploration of GRBs not only deepens our understanding of the universe, but also challenges our knowledge of physics under extreme conditions. In conclusion, gamma ray bursts represent some of the most energetic and mysterious phenomena in the cosmos. They are a testament to the dynamic and often violent nature of the universe, reminding us of the immense forces at play beyond our planet. As we continue to investigate these powerful explosions, we are sure to uncover new insights into the workings of the universe and our place within it. What new discoveries await us in the study of gamma ray bursts? How will they reshape our understanding of the cosmos? The answers to these questions lie in the ongoing exploration of these cosmic beacons. We delved into the fascinating world of gamma ray bursts, which are the most powerful explosions known in the universe. These bursts are incredibly energetic events that occur when massive stars collapse or when neutron stars collide. They release an immense amount of energy in a very short period, often outshining entire galaxies for a brief moment. Understanding gamma ray bursts is crucial because they provide insights into the life cycles of stars and the extreme conditions present in the universe. We shift our focus from these explosive events to a grander scale structure of the universe, the cosmic web. The cosmic web is a vast network that connects galaxies across the universe, forming the large-scale structure of the cosmos. But what exactly is this cosmic web, and how does it shape the universe as we know it? The cosmic web is composed of filaments, nodes, and voids. Filaments are the thread-like structures that stretch across the universe, connecting galaxies and clusters of galaxies. These filaments are primarily made up of dark matter, which is a mysterious and invisible form of matter that does not emit, absorb, or reflect light. Dark matter plays a crucial role in the formation and evolution of the cosmic web, as its gravitational influence helps to pull galaxies and other matter into these filamentary structures. At the intersections of these filaments are nodes, which are dense regions where galaxies and galaxy clusters are concentrated. These nodes are the most massive structures in the universe and are often sites of intense gravitational interactions and galaxy mergers. The cosmic web also contains vast empty regions known as voids, which are areas with very few galaxies. These voids are surrounded by the filaments and nodes, creating a complex and interconnected network. The cosmic web is not a static structure. It is constantly evolving over time. The universe began with the Big Bang, which set the stage for the formation of the cosmic web. In the early universe, matter was distributed relatively evenly, but small fluctuations in density eventually led to the formation of the first structures. Over billions of years, these structures grew and merged under the influence of gravity, forming the intricate cosmic web we observe today. One of the key tools scientists use to study the cosmic web is computer simulations. These simulations allow researchers to model the evolution of the universe from its earliest moments to the present day. By comparing these simulations with observations of the universe, scientists can test their theories about the nature of dark matter and the processes that drive the formation of the cosmic web. Observationally, astronomers use a variety of techniques to map the cosmic web. One common method is to observe the distribution of galaxies across the sky. By measuring the positions and distances of millions of galaxies, astronomers can create three-dimensional maps that reveal the large-scale structure of the universe. Additionally, the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang, provides valuable information about the early universe and the initial conditions that led to the formation of the cosmic web. The cosmic web is not only a fascinating structure in its own right, but it also plays a crucial role in the evolution of galaxies and the universe as a whole. The gravitational interactions within the cosmic web influence the formation and growth of galaxies, as well as the distribution of matter on large scales. Understanding the cosmic web is essential for piecing together the history of the universe and our place within it. As we explore the cosmic web, several intriguing questions arise. How did the cosmic web form, and what role does dark matter play in its evolution? How did the interactions within the cosmic web influence the formation and behavior of galaxies? What can the cosmic web tell us about the fundamental nature of the universe? These questions drive ongoing research and exploration as scientists continue to unravel the mysteries of the cosmic web. By studying this vast and intricate structure, we gain a deeper understanding of the universe and the forces that shape it. The cosmic web is a testament to the complexity and beauty of the cosmos, and it serves as a reminder of the interconnectedness of all things in the universe. We are left with a sense of wonder and curiosity about the cosmic web and its role in the grand tapestry of the universe. What new discoveries await us as we continue to explore this vast and intricate structure? How will our understanding of the cosmic web evolve in the coming years? The journey to uncover the secrets of the universe is far from over, and the cosmic web is a key piece of the puzzle. The cosmic web, we explored the vast and intricate structure that connects galaxies across the universe. This large-scale structure, often referred to as the cosmic web, is a complex network of filaments composed of dark matter and galaxies. These filaments form a web-like pattern that stretches across the cosmos, linking clusters of galaxies together. The cosmic web is a fundamental aspect of the universe's architecture, playing a crucial role in the formation and evolution of galaxies. It is shaped by the gravitational pull of dark matter, which acts as the scaffolding for the visible matter in the universe. Understanding the cosmic web helps scientists gain insights into the distribution of matter in the universe and the forces that govern its dynamics. Now we delve into the fascinating concept of how gravity and speed influence the flow of time. Time dilation is a key principle of Albert Einstein's theory of relativity, which fundamentally changed our understanding of time and space. But what exactly is time dilation, and how does it work? Time dilation refers to the phenomenon where time passes at different rates depending on the relative speed of an observer or the strength of a gravitational field. This means that time is not a constant, universal measure, but can vary based on certain conditions. There are two main types of time dilation: gravitational time dilation and velocity-based time dilation, also known as kinematic time dilation. Gravitational time dilation occurs due to the presence of a massive object, such as a planet, star, or black hole. According to Einstein's theory of general relativity, massive objects warp the fabric of space-time around them. This warping causes time to pass more slowly in stronger gravitational fields compared to weaker ones. For instance, time moves slightly slower on the surface of the Earth compared to a location high above the planet, where the gravitational pull is weaker. This effect, although minuscule, has been measured and confirmed through experiments. One of the most famous examples of gravitational time dilation is the difference in time experienced by astronauts aboard the International Space Station, ISS, compared to people on Earth. The ISS orbits the Earth at a high speed and is also in a weaker gravitational field than the surface of the Earth. As a result, astronauts on the ISS experience time slightly differently than those on the ground. Over the course of a year, this difference amounts to only a fraction of a second, but it is a real and measurable effect. Velocity-based time dilation, on the other hand, occurs when an object is moving at a significant fraction of the speed of light. According to Einstein's theory of special relativity, as an object's speed approaches the speed of light, time for that object slows down relative to a stationary observer. This means that if you were traveling in a spaceship at near light speed, time would pass more slowly for you compared to someone who remains stationary on Earth. This effect becomes more pronounced as the speed increases, highlighting the interconnectedness of time and motion. A classic thought experiment illustrating velocity-based time dilation is the twin paradox. In this scenario, one twin travels on a spaceship at near light speed while the other twin remains on Earth. When the traveling twin returns, they find that they are younger than their sibling who stayed behind. This paradox highlights the non-intuitive nature of time dilation and the profound implications of relativity on our understanding of time. Time dilation has practical implications in our everyday lives, particularly in the realm of technology. One notable example is the Global Positioning System, GPS, which relies on a network of satellites orbiting the Earth. These satellites experience both gravitational and velocity-based time dilation due to their high speeds and positions in weaker gravitational fields. To ensure accurate positioning data, the system must account for these time dilation effects. Without these adjustments, GPS calculations would quickly become inaccurate, leading to errors in navigation. The concept of time dilation also raises intriguing questions about the nature of time itself. If time can be stretched and compressed based on speed and gravity, what does this mean for our perception of time as a constant flow? How do these relativistic effects shape our understanding of the universe and our place within it? As we continue to explore the mysteries of the cosmos, time dilation remains a fundamental aspect of our quest for knowledge. It challenges our perceptions and invites us to reconsider the very fabric of reality. How might future discoveries in physics further illuminate the nature of time? What new technologies could arise from a deeper understanding of time dilation and relativity? These questions remind us that the universe is a vast and wondrous place, full of secrets waiting to be uncovered. We have only scratched the surface of time dilation, a concept that continues to captivate scientists and philosophers alike. As we move forward, we will delve deeper into the implications of time dilation, exploring its role in the broader context of space and time. Join us as we journey further into the enigmatic world of relativity, where the boundaries of time and space are constantly being redefined. What new insights await us in this ever-evolving field of study? The answers may lie just beyond the horizon, waiting to be discovered. In the cosmic theater of the universe, stars are the main actors, and like all actors, they have their entrances and exits. We dive into the fascinating and varied ways in which stars conclude their life cycles. This act is a natural progression from the previous act, time dilation, where we explored how gravity and speed influence the flow of time. Now, we shift our focus from the abstract concept of time to the tangible, albeit grand, phenomena of stellar death. Stars, those brilliant beacons of light in the night sky, are not eternal. They are born, they live, and eventually they die. But how exactly does a star die? The answer to this question depends largely on the star's mass. The mass of a star is the key determinant of its life cycle and its eventual demise. Let's explore the different paths a star might take as it reaches the end of its life. For stars like our Sun, which are considered to be of average mass, the end of life is relatively peaceful. These stars spend the majority of their lives fusing hydrogen into helium in their cores, a process that releases energy and keeps the star shining. However, once the hydrogen in the core is exhausted, the star enters the next phase of its life. It expands into a red giant, a phase where the outer layers swell and the core contracts. During this red giant phase, the star begins to fuse helium into heavier elements like carbon and oxygen. Eventually, the outer layers of the red giant are expelled, creating a beautiful shell of gas known as a planetary nebula. What remains of the star is the core, which becomes a white dwarf. A white dwarf is a dense, hot remnant that slowly cools and fades over time. It no longer undergoes fusion reactions and will eventually become a cold, dark object known as a black dwarf, though the universe is not old enough for any black dwarfs to exist yet. But what about stars that are much more massive than the Sun? These stars have a more dramatic end. Massive stars also begin their lives by fusing hydrogen into helium, but they do so at a much faster rate due to their greater mass and gravitational pressure. Once the hydrogen is depleted, these stars go through a series of stages, fusing heavier and heavier elements in their cores. This process continues until iron is formed. Iron is the end of the line for fusion because it does not release energy when fused. When a massive star's core is primarily iron, it can no longer support the star against gravitational collapse. The core collapses rapidly, and the outer layers are blown away in a catastrophic explosion known as a supernova. A supernova is one of the most energetic events in the universe, briefly outshining entire galaxies. The remnants of the core can become either a neutron star or a black hole, depending on the mass of the core. A neutron star is an incredibly dense object composed mostly of neutrons. It is so dense that a sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. If the core is even more massive, it can collapse further to form a black hole, an object with gravity so strong that not even light can escape from it. There are also stars that are less massive than the Sun. These stars, known as red dwarfs, have much longer lifespans. They burn their fuel very slowly and can last for trillions of years. Because the universe is only about 13.8 billion years old, no red dwarf has yet reached the end of its life. However, it is believed that they will eventually become white dwarfs as well, after exhausting their nuclear fuel. The death of a star is not just an end, but also a beginning. The materials expelled during the death of stars, especially in supernovae, enrich the surrounding space with heavy elements. These elements are the building blocks of planets and life itself. In this way, stellar death contributes to the cycle of cosmic evolution, leading to the formation of new stars and planetary systems. In summary, the death of a star is a complex process that depends on its mass. Average stars like the Sun end their lives as white dwarfs after shedding their outer layers as planetary nebulae. Massive stars explode as supernovae, leaving behind neutron stars or black holes. Less massive stars, like red dwarfs, have not yet reached the end of their life cycles. Each type of stellar death plays a crucial role in the cosmic ecosystem, recycling materials and paving the way for new generations of stars and planets. As we gazed up at the night sky, we are reminded of the dynamic and ever-changing nature of the universe, where even the most brilliant stars must eventually fade away. In the previous act, Stellar Death, we explored the fascinating and varied ways in which stars conclude their life cycles. From the gentle fading of a white dwarf to the cataclysmic explosion of a supernova, the death of a star is a process that can lead to the creation of new elements and even new stars. This act set the stage for understanding the life cycle of celestial bodies and the ongoing cycle of creation and destruction in the universe. We delve into one of the most intriguing and fundamental questions of cosmology. Why does our universe exist in its current form? This act focuses on the cosmic asymmetry between matter and antimatter, a phenomenon that has puzzled scientists for decades. To understand this cosmic asymmetry, we must first grasp what matter and antimatter are. Matter is composed of particles such as protons, neutrons, and electrons, which make up the atoms that form everything we see around us. Antimatter, on the other hand, is made up of antiparticles, which are the counterparts to these particles. For instance, the antiparticle of an electron is a positron, which has the same mass as an electron but an opposite charge. When matter and antimatter meet, they annihilate each other in a burst of energy, a process that is both fascinating and fundamental to the laws of physics. According to the Big Bang Theory, the universe began with equal amounts of matter and antimatter. So, why is there so much more matter than antimatter in the universe today? This imbalance is known as baryon asymmetry, and it is one of the biggest mysteries in physics. If matter and antimatter were created in equal amounts, they should have annihilated each other completely, leaving behind a universe filled only with energy. Yet, here we are in a universe dominated by matter. What could have caused this imbalance? One possible explanation is the concept of CP violation, which refers to the violation of the combined symmetry of charge conjugation, C, and parity, PD. In simpler terms, CP violations suggest that the laws of physics might not apply equally to matter and antimatter. This idea was first observed in the 1960s in experiments involving particles known as kaons, which showed that certain reactions involving these particles did not behave the same way when matter was replaced with antimatter. The discovery of CP violation was groundbreaking because it suggested a mechanism by which the universe could have developed a preference for matter over antimatter. However, the amount of CP violation observed in experiments is not sufficient to account for the vast imbalance we see today. This has led scientists to search for additional sources of CP violation in other particles and interactions. Another intriguing possibility is the existence of a process known as leptogenesis. This theory suggests that the asymmetry between matter and antimatter could have originated from the decay of heavy neutrinos in the early universe. Neutrinos are elusive particles that interact very weakly with matter, making them difficult to study. However, their behavior could hold the key to understanding the matter-antimatter imbalance. The Large Hadron Collider, LHC, the world's largest and most powerful particle accelerator, has been instrumental in probing these questions. By recreating the conditions of the early universe in high-energy collisions, scientists hope to uncover new particles and interactions that could explain the dominance of matter over antimatter. The matter-antimatter asymmetry is not just a theoretical curiosity. It has profound implications for our understanding of the universe. If the balance had been different, if antimatter had dominated instead of matter, the universe as we know it would not exist. Galaxies, stars, planets, and even life itself might never have formed. As we continue to explore the mysteries of matter and antimatter, we are reminded of the delicate balance that allows our universe to exist. What other secrets might the universe hold? Could there be regions of space where antimatter is more prevalent than matter? How might future discoveries reshape our understanding of the cosmos? The quest to understand the matter-antimatter asymmetry is a journey into the heart of the universe's origins. It challenges us to question our assumptions and to seek answers to some of the most profound questions about our existence. As we move forward, we remain on the brink of discovery, poised to uncover the fundamental truths that govern our universe. What will the next chapter in this cosmic story reveal? We delved into the intriguing concept of matter versus antimatter, a cosmic asymmetry that played a crucial role in the existence of our universe. We explored how, in the early universe, matter and antimatter were created in almost equal amounts. However, a slight imbalance favored matter, which allowed the universe as we know it to exist. This asymmetry is what prevented the universe from annihilating itself into pure energy, leaving behind the matter that forms stars, planets, and ultimately life. We turn our attention to another pivotal event in the history of the universe: cosmic inflation. This act focuses on the rapid expansion of space that occurred in the universe's first fraction of a second. But what exactly is cosmic inflation, and why is it so significant? Cosmic inflation is a theory that suggests the universe underwent an exponential expansion in its earliest moments. Imagine the universe as a tiny, dense point, smaller than an atom. In an incredibly brief period, less than a trillionth of a second, this point expanded to a size many times larger. This expansion was not just fast, it was unimaginably fast, faster than the speed of light. But how could this be possible, given that nothing can travel faster than light? The key to understanding this lies in the nature of space itself. During inflation, it wasn't matter or energy moving through space that expanded so rapidly, but space itself that stretched. This distinction is crucial because the speed of light limit applies to objects moving through space, not to the expansion of space itself. As space expanded, it carried with it the nascent universe, smoothing out any irregularities and setting the stage for the formation of galaxies and other cosmic structures. One might wonder what triggered this rapid expansion. The exact mechanism behind cosmic inflation is still a topic of research and debate among scientists. However, it is generally believed that a high-energy field, often referred to as the inflating field, was responsible for driving this expansion. As the universe expanded, this field lost energy, which was then converted into the particles and radiation that filled the universe. Cosmic inflation helps explain several puzzling observations about the universe. For instance, it accounts for the universe's large-scale uniformity. When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that it is remarkably uniform in all directions. Without inflation, different regions of the universe would not have been in contact long enough to reach such a uniform temperature. Inflation solves this by suggesting that these regions were once close together before being rapidly stretched apart. Another mystery addressed by inflation is the flatness of the universe. Observations suggest that the universe is geometrically flat, meaning that parallel lines will never meet. Inflation predicts this flatness because the rapid expansion would have smoothed out any initial curvature, much like how a balloon appears flatter as it is inflated. Furthermore, inflation provides a framework for understanding the distribution of galaxies and large-scale structures in the universe. Tiny quantum fluctuations during the inflationary period were stretched to cosmic scales, seeding the formation of galaxies and clusters of galaxies. These fluctuations are imprinted in the cosmic microwave background as slight temperature variations, which have been observed by satellites like the Cosmic Background Explorer, COBE, and the Planck spacecraft. Despite its explanatory power, cosmic inflation is not without its challenges and open questions. One of the biggest challenges is identifying the nature of the inflating field and understanding its properties. Additionally, there are various models of inflation, each with different predictions about the universe's early moments. Scientists continue to refine these models and test their predictions against observations. As we explore the concept of cosmic inflation, it is important to consider its implications for our understanding of the universe. If inflation occurred, it suggests that the universe we observe is just a small part of a much larger and possibly infinite cosmos. This raises questions about the nature of reality and our place within it. Could there be other regions of the universe, or even other universes, that underwent different inflationary histories? Cosmic inflation is a fascinating and complex topic that challenges our understanding of the universe's origins. It invites us to ponder profound questions about the nature of space, time, and the very fabric of reality. As we continue to investigate this early chapter of the universe's history, we are reminded of the vastness and mystery of the cosmos and the ongoing quest to unravel its secrets. Cosmic inflation takes us on a journey to the universe's earliest moments, exploring a period of rapid expansion that shaped the cosmos we observe today. It builds on the foundation laid in Act 19, where the matter-antimatter asymmetry allowed the universe to exist. Together, these acts provide a deeper understanding of the universe's origins and the forces that have shaped its evolution. As we move forward, we will continue to explore the wonders of the cosmos, seeking to uncover the mysteries that lie at the heart of existence. We delve into the fascinating realm of exoplanets, which are planets located outside our solar system. This act explores the discovery of these distant worlds and the incredible diversity they exhibit, expanding our understanding of the universe and our place within it. But what exactly are exoplanets, and how did we come to know about them? The journey of discovering exoplanets began in earnest in the late 20th century. Before this time, the existence of planets beyond our solar system was purely speculative. However, with advancements in technology and observational techniques, astronomers were able to detect these elusive celestial bodies. The first confirmed detection of an exoplanet occurred in 1992 when astronomers Alexander Wolszczan and Dale Frail discovered planets orbiting a pulsar, a type of neutron star, using radio wave observations. This groundbreaking discovery opened the floodgates for further exploration. One of the most significant breakthroughs in exoplanet discovery came in 1995 when Swiss astronomers Michael Mayer and Didier Queloz announced the discovery of 51 Pegasi, the first exoplanet found orbiting a sun-like star. This discovery was made using the radial velocity method, which detects variations in the velocity of a star due to the gravitational pull of an orbiting planet. The discovery of 51 Pegasi was a pivotal moment in astronomy, proving that planets could indeed exist around stars similar to our Sun. Since then, the search for exoplanets has intensified, with thousands of these distant worlds being discovered. One of the key instruments in this quest has been the Kepler Space Telescope, launched by NASA in 2009. Kepler's mission was to survey a portion of our galaxy to discover Earth-sized exoplanets in or near the habitable zone, the region around the star where conditions might be right for liquid water to exist. Kepler used the transit method, which involves detecting the slight dimming of a star's light as a planet passes in front of it. This method has been incredibly successful, leading to the discovery of over 2,600 confirmed exoplanets. The diversity of exoplanets discovered is truly astonishing. They come in a wide range of sizes, compositions, and orbital characteristics. Some exoplanets, known as hot Jupiters, are gas giants that orbit very close to their host stars, resulting in extremely high surface temperatures. Others, like super-Earths, are rocky planets larger than Earth but smaller than Neptune, with varying potential for habitability. There are also mini Neptunes, which are smaller than Neptune but have thick gaseous atmospheres. One of the most intriguing aspects of exoplanet research is the search for potentially habitable worlds. Scientists are particularly interested in finding exoplanets within the habitable zone of their stars, where conditions might allow for the presence of liquid water, a key ingredient for life as we know it. The discovery of such planets raises exciting possibilities about the existence of life beyond Earth. The study of exoplanet atmospheres has also become a crucial area of research. By analyzing the light that passes through an exoplanet's atmosphere during a transit, scientists can determine its composition. This information can reveal the presence of gases like water vapor, carbon dioxide, and methane, which are important for understanding the planet's potential habitability and climate. The diversity of exoplanets also challenges our understanding of planetary formation and evolution. Traditional models of planet formation, based on our solar system, are being reevaluated in light of the diverse exoplanetary systems discovered. For instance, the existence of hot Jupiters, which orbit very close to their stars, suggests that planetary migration may play a significant role in shaping planetary systems. As we continue to discover and study exoplanets, new questions arise. How common are Earth-like planets in the galaxy? What are the conditions necessary for life to develop on these distant worlds? Are there other forms of life that exist in environments vastly different from our own? These questions drive the ongoing research and exploration in the field of exoplanetary science. Exoplanet Symphony highlights the remarkable progress made in the discovery and study of exoplanets. From the first detections in the 1990s to the thousands of diverse worlds known today, our understanding of the universe has been profoundly enriched. The search for exoplanets not only expands our knowledge of planetary systems, but also fuels our curiosity about the potential for life beyond Earth. As technology and techniques continue to advance, the symphony of exoplanetary discovery will undoubtedly play on, revealing new and exciting chapters in the story of the cosmos. We embark on an exploration of some of the most fascinating and luminous objects in the universe, quasars. These celestial phenomena are not just bright. They are the brightest objects known to exist, outshining entire galaxies. But what exactly are quasars, and what makes them so incredibly luminous? To understand quasars, we must first delve into the heart of galaxies where they are found. At the center of many galaxies, including our own Milky Way, lies a supermassive black hole. These black holes are millions to billions of times more massive than our Sun. But how did these black holes, known for their light-trapping properties, relate to the brilliance of quasars? The answer lies in the accretion of material. As matter, such as gas and dust, spirals towards a supermassive black hole, it forms what is known as an accretion disk. This disk is a swirling mass of material that heats up to extreme temperatures due to friction and gravitational forces. As the material heats up, it emits enormous amounts of energy, particularly in the form of light. This is what we observe as a quasar. Quasars are not just bright. They are incredibly distant, often located billions of light years away from Earth. This means that when we observe a quasar, we are looking back in time, seeing the universe as it was billions of years ago. This makes quasars valuable tools for astronomers studying the early universe and the formation of galaxies. One might wonder, how were quasars first discovered? The story begins in the 1960s when astronomers using radio telescopes detected mysterious radio sources that did not correspond to any known stars or galaxies. Optical telescopes later revealed these sources as point-like objects, similar in appearance to stars, but with peculiar spectral lines. These spectral lines indicated that the objects were moving away from us at incredible speeds, suggesting they were located at vast distances. The term quasar is derived from quasi-stellar radio source, reflecting their star-like appearance and radio emissions. However, not all quasars emit strong radio waves. Those that do are known as radio-loud quasars, while those that do not are called radio-quiet quasars. The study of quasars has led to significant advancements in our understanding of the universe. For instance, quasars have been used to map the distribution of matter in the universe, as their light passes through intergalactic space, revealing the presence of otherwise invisible gas clouds. Additionally, quasars provide insights into the growth and evolution of supermassive black holes and their host galaxies. But what powers these supermassive black holes to create such luminous quasars? The energy output of a quasar is immense, often exceeding that of hundreds of galaxies combined. This energy is primarily generated by the gravitational forces at play as material falls into the black hole. The conversion of gravitational energy into light and other forms of radiation is incredibly efficient, making quasars some of the most energetic phenomena in the universe. Quasars also exhibit variability in their brightness, sometimes changing over the course of days, weeks, or even years. This variability is thought to be caused by changes in the rate of accretion or by the presence of structures within the accretion disk, such as hot spots or jets of material being ejected at near-light speeds. The jets emitted by some quasars are another intriguing aspect. These jets are streams of charged particles that are propelled away from the black hole at relativistic speeds, often extending thousands of light years into space. These jets can interact with the surrounding intergalactic medium, influencing the formation of stars and the evolution of galaxies. As we continue our quest to understand quasars, New technologies and telescopes are providing unprecedented views of these distant objects. Instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope allow astronomers to study quasars in greater detail, unraveling the mysteries of their formation and evolution. In summary, quasars are not only the brightest objects in the universe, but also key to unlocking the secrets of the cosmos. They offer a glimpse into the early universe, the nature of supermassive black holes, and the intricate dance of matter and energy on the grandest scales. As we continue to explore these luminous beacons, what new discoveries await us in the vast expanse of space? What do quasars tell us about the universe's past, and how might they shape our understanding of its future? The quest for answers continues as the universe beckons us to look deeper and further than ever before. We explored the fascinating world of quasars, the brightest objects in the universe. These celestial phenomena are powered by supermassive black holes located at the centers of distant galaxies. As matter spirals into these black holes, it heats up and emits enormous amounts of energy, making quasars visible across vast cosmic distances. Quasars serve as beacons, illuminating the far reaches of the universe and providing insights into the early stages of galaxy formation. They are not just astronomical wonders, but also essential tools for understanding the cosmos. This part delves into the mysterious and energetic particles known as cosmic rays, which originate from beyond our solar system. But what exactly are cosmic rays, and why are they significant? Cosmic rays are high-energy particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. These particles are not rays in the traditional sense, like light rays, but rather individual particles that bombard the Earth from all directions. Their origins are diverse, with some coming from the Sun, while others originate from more distant sources such as supernovae, quasars, and even the remnants of ancient stars. One of the most intriguing aspects of cosmic rays is their energy. Some cosmic rays possess energy levels millions of times greater than those produced by the most powerful particle accelerators on Earth. This raises the question: what cosmic processes are capable of accelerating particles to such extreme energies? The journey of cosmic rays begins in the depths of space. When a star explodes in a supernova, it releases an immense amount of energy, propelling particles into space at incredible speeds. These particles, now cosmic rays, travel through the galaxy, occasionally colliding with other particles or magnetic fields, which can further accelerate them. This process, known as Fermi acceleration, is one of the primary mechanisms believed to be responsible for the high energies of cosmic rays. As cosmic rays traverse the galaxy, they encounter various obstacles, such as interstellar magnetic fields and cosmic dust. These interactions can alter their paths, making it challenging to trace their origins. However, by studying the composition and energy of cosmic rays, scientists can glean valuable information about the environments and processes that produce them. Upon reaching Earth, cosmic rays interact with the planet's atmosphere, creating showers of secondary particles. These secondary particles can be detected by ground-based observatories and space-based instruments, allowing scientists to study cosmic rays indirectly. One of the most famous observatories dedicated to studying cosmic rays is the Pierre Auger Observatory in Argentina, which uses an array of detectors spread over a large area to capture and analyze these particle showers. Cosmic rays have significant implications for both science and technology. For instance, they play a crucial role in the formation of clouds and the Earth's climate. By ionizing atmospheric molecules, cosmic rays can influence cloud condensation processes, potentially affecting weather patterns. Furthermore, cosmic rays pose a challenge for space travel. High-energy particles can damage spacecraft electronics and pose health risks to astronauts, making it essential to understand and mitigate their effects for future space missions. The study of cosmic rays also intersects with other areas of physics, such as particle physics and astrophysics. By examining cosmic rays, scientists can test theories about the fundamental forces of nature and the structure of the universe. For example, cosmic rays may provide insights into dark matter, a mysterious substance that makes up a significant portion of the universe's mass, but remains undetected through conventional means. In conclusion, cosmic rays are more than just high-energy particles zipping through space. They are a window into the energetic processes of the universe, offering clues about the origins and evolution of cosmic phenomena. As we continue to study these enigmatic particles, we may unlock new secrets about the universe and our place within it. What new discoveries await us in the realm of cosmic rays? How will our understanding of these particles shape the future of space exploration and scientific inquiry? The quest for answers continues as we delve deeper into the mysteries of the cosmos. We explore the fascinating world of high-energy particles that originate from beyond our solar system. These cosmic rays, composed primarily of protons and atomic nuclei, travel through space at nearly the speed of light. They are intriguing because they carry information about the most energetic and violent processes in the universe, such as supernovae, black holes, and even the Big Bang itself. Scientists study cosmic rays to understand these cosmic events and the fundamental forces that govern the universe. But as we move forward, we turn our attention to another enigmatic aspect of the cosmos, the energy that exists in the very fabric of space itself. This act delves into the mysterious energy that permeates empty space, a concept that challenges our understanding of the universe. But what exactly is vacuum energy, and why is it so important? To begin with, let's consider what we mean by empty space. In classical physics, a vacuum is simply a space devoid of matter. However, modern physics, particularly quantum mechanics, reveals that even in a perfect vacuum, space is not truly empty. Instead, it is teeming with activity at the quantum level. This leads us to the concept of vacuum energy, which is the energy present in this so-called empty space. The idea of vacuum energy arises from the principles of quantum field theory, which suggests that particles and antiparticles are constantly being created and annihilated in empty space. This constant fluctuation gives rise to a baseline level of energy, even in the absence of matter. This energy is what we refer to as vacuum energy. One of the most intriguing aspects of vacuum energy is its potential connection to the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. The cosmological constant was initially proposed as a way to achieve a static universe, but it was later abandoned when it was discovered that the universe is expanding. However, the concept resurfaced with the discovery of the accelerated expansion of the universe, leading scientists to propose that vacuum energy might be responsible for this acceleration. Could vacuum energy be the driving force behind the mysterious dark energy that makes up approximately 68% of the universe? This is one of the most significant questions in modern cosmology. Dark energy is thought to be responsible for the accelerated expansion of the universe, and vacuum energy is a leading candidate for its source. However, the exact nature of dark energy and its relationship to vacuum energy remains one of the greatest mysteries in physics. Another fascinating aspect of vacuum energy is its implications for the concept of zero-point energy. Zero-point energy refers to the lowest possible energy that a quantum mechanical system may have, and it is a direct consequence of the Heisenberg uncertainty principle. In simple terms, even at absolute zero, where all classical motion ceases, quantum systems still possess some intrinsic energy. This zero-point energy is closely related to vacuum energy and has been a topic of interest for both theoretical and practical reasons. The concept of vacuum energy also raises questions about the stability of the universe. If vacuum energy is indeed a fundamental property of space, what does that mean for the future of the universe? Some theories suggest that changes in vacuum energy could lead to dramatic cosmic events, such as the collapse of the universe or the creation of new universes. These ideas, while speculative, highlight the profound implications that vacuum energy has for our understanding of the cosmos. Moreover, vacuum energy is not just a theoretical construct, it has observable effects. One of the most well-known manifestations of vacuum energy is the Casimir effect, named after Dutch physicist Hendrik Casimir. The Casimir effect occurs when two uncharged, parallel plates are placed very close to each other in a vacuum. Due to the vacuum fluctuations between the plates, an attractive force is generated, pulling the plates together. This effect provides experimental evidence for the existence of vacuum energy and demonstrates its influence on physical objects. As we delve deeper into the mysteries of vacuum energy, we encounter more questions than answers. How does vacuum energy interact with other forms of energy and matter? What role does it play in the fundamental structure of the universe? And how can we reconcile the theoretical predictions of vacuum energy with the observed properties of the universe? These questions drive ongoing research in both theoretical and experimental physics. Scientists are developing new models and conducting experiments to better understand the nature of vacuum energy and its implications for the universe. Advances in technology, such as more sensitive detectors and more powerful particle accelerators, are helping researchers probe the quantum realm and uncover the secrets of vacuum energy. In conclusion, vacuum energy is a captivating and complex topic that challenges our understanding of the universe. It is a reminder of the profound mysteries that still await discovery in the cosmos. As we continue to explore the nature of vacuum energy, we are not only seeking answers to fundamental questions about the universe, but also expanding the boundaries of human knowledge. What new insights will we uncover in the quest to understand this mysterious energy? Only time will tell, but one thing is certain. The journey promises to be as fascinating as the destination. We delve into the fascinating odyssey of photons as they traverse the vast expanse of the cosmos. This journey is not just a simple trip from point A to point B. It is a complex voyage that spans billions of years, crossing unimaginable distances and encountering various cosmic phenomena along the way. But what exactly are photons, and how do they manage to travel such immense distances? Photons are elementary particles, the fundamental units of light and all other forms of electromagnetic radiation. They are massless, which allows them to travel at the speed of light, approximately 299,792 kilometers per second, or about 186,282 miles per second in a vacuum. This incredible speed is what enables photons to journey across the universe, covering vast distances that would be impossible for anything with mass to traverse in a reasonable time frame. The journey of a photon begins at its source, which could be anything from a distant star, a galaxy, or even the remnants of the Big Bang itself. When we look up at the night sky, the light we see from stars and galaxies has often traveled for millions or even billions of years before reaching our eyes. This means that when we observe these celestial objects, we are actually looking back in time, seeing them as they were when the light first left them. One of the most intriguing aspects of a photon's journey is how it interacts with the universe's expanding nature. The universe has been expanding since the Big Bang, and this expansion affects the light traveling through it. As photons move through space, they experience a phenomenon known as redshift. This occurs because the expansion of the universe stretches the wavelength of the light, shifting it towards the red end of the spectrum. The greater the distance a photon travels, the more redshifted it becomes. This redshift provides astronomers with crucial information about the universe's expansion rate and the distance of celestial objects. But what challenges do photons face on their journey? One significant obstacle is the presence of interstellar and intergalactic matter. Although space is mostly empty, it is not a perfect vacuum. Photons can encounter particles such as dust, gas, and cosmic rays, which can scatter or absorb them. This interaction can alter the photon's path or even prevent it from reaching its destination. Despite these challenges, many photons still manage to traverse the cosmos, providing us with valuable information about the universe. Another interesting aspect of a photon's journey is its interaction with gravitational fields. According to Einstein's theory of general relativity, massive objects like stars and galaxies warp the fabric of space-time around them. This warping affects the path of photons, causing them to bend as they pass near these massive objects. This phenomenon, known as gravitational lensing, can magnify and distort the images of distant objects, allowing astronomers to study them in greater detail. Photons also play a crucial role in the cosmic microwave background, CMB radiation, which is the afterglow of the Big Bang. The CMB is composed of photons that have been traveling through the universe since shortly after the Big Bang, approximately 13.8 billion years ago. These ancient photons provide a snapshot of the early universe, offering insights into its initial conditions and subsequent evolution. The journey of light across the cosmos is not just a scientific curiosity. It has profound implications for our understanding of the universe. By studying the light from distant objects, astronomers can learn about the composition, structure, and history of the universe. Light's journey also raises intriguing questions about the nature of time and space. How does the finite speed of light affect our perception of the universe? What can the redshift of light tell us about the fate of the universe? And how do photons manage to convey so much information across such vast distances? As we continue to explore the universe, the journey of light remains a central theme in our quest for knowledge. The photons that reach us from distant corners of the cosmos are like messengers from the past, carrying with them the secrets of the universe's history and evolution. By unraveling these secrets, we can gain a deeper understanding of our place in the cosmos and the forces that have shaped it over billions of years. We explored the fascinating voyage of photons as they traverse the vast expanses of the cosmos, sometimes for billions of years. This journey of light is not only a testament to the immense scale of the universe, but also a crucial process that allows us to observe and understand the cosmos. Photons, the fundamental particles of light, are emitted by stars and other celestial objects. They travel across the universe, often covering unimaginable distances before reaching our telescopes and eyes. This act delved into the mechanisms by which light travels, the speed at which it moves, and the interactions it may encounter along the way, such as scattering, absorption, and redshift. These interactions can alter the light's path and characteristics, providing us with valuable information about the universe's structure and history. We shift our focus from the journey of light to the stars themselves, specifically the different generations of stars that populate our universe. Stars are not static entities. They are born, evolve, and eventually die, contributing to the cosmic cycle of matter and energy. But did you know that not all stars are created equal? In fact, stars can be categorized into different populations based on their age, composition, and formation history. Understanding these stellar populations is key to unraveling the history of our universe and the processes that have shaped it over billions of years. The concept of stellar populations was first introduced in the mid-20th century when astronomers began to notice differences in the star's properties within our galaxy, the Milky Way. These differences were not random, but rather indicative of distinct groups or generations of stars. Broadly, stars are classified into three main populations: Population I, Population II, and Population ILA stars. Each of these populations tells a unique story about the universe's evolution. Population I stars are the youngest stars in the universe. They are typically found in the spiral arms of galaxies, like our own Milky Way, and are rich in metals. In astronomical terms, metals refer to elements heavier than hydrogen and helium. These stars have formed from the remnants of previous generations of stars, incorporating the heavier elements produced by those stars' nuclear fusion processes. As a result, Population I stars, like our Sun, are metal-rich and often associated with regions of active star formation. In contrast, Population ILA stars are older and have a lower metal content. These stars are generally found in the halo of galaxies and in globular clusters, which are dense groups of stars that orbit the galactic core. The lower metal content of Population ILA stars suggests that they formed earlier in the universe's history, before many of the heavier elements were synthesized in the cores of stars. Studying these stars provides astronomers with insights into the early stages of galaxy formation and the conditions of the early universe. The most intriguing and elusive of all are the Population ILA stars. These are the first generation of stars, formed from the primordial gas composed almost entirely of hydrogen and helium, the elements created in the Big Bang. Population ILI stars are thought to be massive and short-lived, burning through their nuclear fuel quickly and ending their lives in spectacular supernova explosions. These explosions would have seeded the universe with the first heavy elements, setting the stage for the formation of later generations of stars. However, no population ILI stars have been observed directly, as they are believed to have existed only in the very early universe. Their existence is inferred from theoretical models and the chemical composition of later generation stars. The study of stellar populations is not just about classifying stars. It is a window into the past, allowing us to piece together the history of our galaxy and the universe. By examining the distribution and properties of different stellar populations, astronomers can trace the processes of star formation, galaxy evolution, and chemical enrichment over cosmic time. This knowledge helps us understand how galaxies like the Milky Way have evolved and how the elements necessary for life have been distributed throughout the universe. We will explore how astronomers identified and studied these stellar populations. What techniques do they use to determine a star's age and composition? How do they differentiate between the various populations? And what do these stars tell us about the universe's past, present, and future? Join us as we uncover the secrets of the stars and the stories they have to tell about the cosmos. We explore an intriguing concept that compresses the vast history of the universe into the span of a single Earth year. This imaginative framework, often referred to as the cosmic calendar, was popularized by the renowned astrophysicist Carl Sagan. It serves as a powerful tool to help us grasp the immense timescales involved in the universe's history by relating them to a more familiar, manageable time frame. Imagine the entire 13.8 billion year history of the universe condensed into just 365 days. This analogy allows us to visualize and understand the sequence of cosmic events in a way that is both accessible and engaging. By doing so, we can better appreciate the relative timing of significant occurrences in the universe's timeline. Let's begin our journey through the cosmic calendar. On this scale, the Big Bang, which marks the birth of the universe, occurs at precisely midnight on January 1st. This monumental event set the stage for everything that followed, as the universe began its rapid expansion and cooling. In the first few moments after the Big Bang, fundamental particles formed, eventually leading to the creation of atoms. As we move through the first few months of the cosmic calendar, we witness the formation of the first stars and galaxies. By early March, the Milky Way galaxy, our cosmic home, begins to take shape. These early stars, known as population ILI stars, were massive and short-lived, contributing to the enrichment of the universe with heavier elements through supernova explosions. Fast forward to late August, and we find ourselves in a universe that has evolved significantly. By this time, our solar system is forming. The Sun, along with its planets, including Earth, comes into existence around September 1st. This marks a crucial point in the cosmic calendar as our planet begins its journey through time. As we continue through the months, life on Earth emerges. Simple life forms appear in the oceans around late September. These early organisms are the ancestors of all life on our planet. The development of more complex life forms, such as multicellular organisms, occurs in mid-December. The cosmic calendar also highlights the relatively recent appearance of humans in the grand scheme of the universe's history. It is only in the final moments of December 31st that modern humans make their appearance. To put this into perspective, the entirety of human history, from the earliest civilizations to the present day, occupies just the last few seconds of the cosmic calendar. This perspective is both humbling and awe-inspiring. It reminds us of the vastness of the universe and the brief moment in which humanity has existed. It also prompts us to consider the potential future of our species and the universe itself. What might the next year on the cosmic calendar hold? How will our actions today shape the future of our planet and beyond? The cosmic calendar serves as a reminder of our place in the universe and the interconnectedness of all things. It encourages us to reflect on the journey of the cosmos and our role within it. As we ponder these questions, we are invited to explore the mysteries of the universe further and to seek a deeper understanding of our origins and destiny. In conclusion, the cosmic calendar is a powerful tool that allows us to comprehend the vast history of the universe in a relatable and engaging way. By compressing billions of years into a single year, we gain a greater appreciation for the sequence of cosmic events and our place within this grand narrative. As we continue to explore the universe, let us carry with us the insights and inspiration offered by the cosmic calendar, and let it guide us in our quest for knowledge and understanding. We delve into the fascinating concept of how gravity influences the very structure of our universe. To understand this, we must first grasp the idea of space-time itself. Space-time is a four-dimensional construct that combines the three dimensions of space with the dimension of time into a single interwoven continuum. This concept was revolutionary, introduced by Albert Einstein in his theory of general relativity. Einstein proposed that massive objects, like planets and stars, do not just exist in space, but actually warp the fabric of space-time around them. Imagine space-time as a flexible sheet, like a trampoline. When a heavy object, such as a bowling ball, is placed on the trampoline, it creates a depression. Similarly, massive objects in the universe create curves in the space-time fabric. This curvature is what we perceive as gravity. But how does this warping of space-time affect objects around these massive bodies? According to Einstein, objects move along the paths dictated by the curvature of space-time. This means that what we traditionally think of as the force of gravity is actually the result of objects following the natural curves in the space-time fabric. For instance, the Earth orbits the Sun not because it is being pulled by an invisible force, but because it is following the curved path in the space-time created by the Sun's mass. This concept challenges the Newtonian view of gravity, which described it as a force acting at a distance. Einstein's theory, however, provides a more comprehensive explanation by illustrating that gravity is not just a force, but a geometric property of space-time itself. This idea has profound implications for our understanding of the universe. One of the most intriguing consequences of the warping of space-time is the phenomenon of time dilation. Time dilation refers to the difference in the passage of time as experienced by observers in different gravitational fields. In regions of strong gravitational fields, such as near a massive star or a black hole, time passes more slowly compared to regions with weaker gravitational fields. This means that if you were to spend time near a massive object, you would age more slowly relative to someone who remained in a region with less gravitational influence. The concept of space-time warping also leads us to the fascinating objects known as black holes. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. They are formed when massive stars collapse under their own gravity, compressing their mass into an incredibly small volume. This results in a singularity, a point where the curvature of space-time becomes infinite. The boundary surrounding a black hole is called the event horizon, beyond which nothing can return. The study of space-time and gravity has also led to the prediction and discovery of gravitational waves. These are ripples in the fabric of space-time caused by the acceleration of massive objects, such as when two black holes collide. Gravitational waves were first predicted by Einstein in 1916, but it wasn't until 2015 that they were directly detected by the LIGO Observatory. This discovery opened a new window into the universe, allowing us to observe cosmic events that were previously invisible. As we explore the concept of space-time fabric, we must also consider its implications for the future of space travel. The warping of space-time suggests the possibility of phenomena like wormholes, theoretical passages through space-time that could create shortcuts between distant parts of the universe. While purely speculative at this point, the idea of wormholes captivates the imagination and challenges our understanding of the cosmos. In conclusion, the concept of space-time fabric and its warping by gravity provides a profound insight into the workings of our universe. It challenges our traditional notions of gravity and offers a more comprehensive framework for understanding the cosmos. As we continue to explore these ideas, we are left with intriguing questions. How can we further test and observe the warping of space-time? What new discoveries await us in the realm of gravitational waves? Could the concept of wormholes ever become a reality? The exploration of space-time fabric not only deepens our understanding of the universe, but also inspires us to continue seeking answers to the mysteries that lie beyond our current knowledge. We delve into the fascinating and complex processes that govern the growth and transformation of galaxies over billions of years. This act builds upon the foundational understanding of the universe's structure, as explored in the previous act, Space-Time Fabric, where we examined how gravity influences the four-dimensional fabric of our universe. Now, we shift our focus to the cosmic entities that populate this vast expanse, galaxies. Galaxies are massive systems composed of stars, stellar remnants, interstellar gas, dust, and dark matter, all bound together by gravity. They are the fundamental building blocks of the universe, and their evolution is a key area of study in astrophysics. But how did these colossal structures form? And what processes drive their evolution over time? The story of galaxy evolution begins shortly after the Big Bang, approximately 13.8 billion years ago. In the early universe, matter was not uniformly distributed. Instead, slight density fluctuations existed, which were the seeds for galaxy formation. Over time, these fluctuations grew under the influence of gravity, leading to the formation of the first stars and galaxies. The initial stage of galaxy formation is often referred to as the Dark Ages, a period before the first stars ignited. During this time, the universe was filled with neutral hydrogen gas. As gravity pulled matter together, the first stars, known as population Ia stars, began to form. These stars were massive and short-lived, and their deaths in supernova explosions enriched the surrounding gas with heavier elements, setting the stage for the formation of subsequent generations of stars and galaxies. As galaxies formed and evolved, they underwent various processes that shaped their structure and composition. One of the key processes is mergers, where two or more galaxies collide and combine to form a single, larger galaxy. These mergers play a crucial role in galaxy evolution, often triggering bursts of star formation and altering the galaxy's shapes and sizes. For instance, our own Milky Way galaxy is believed to have undergone numerous mergers throughout its history, contributing to its current structure. Another important aspect of galaxy evolution is the role of dark matter. Although it does not emit or absorb light, dark matter exerts gravitational forces that influence the dynamics of galaxies. It forms a halo around galaxies, providing the gravitational scaffolding necessary for their formation and stability. Understanding the distribution and behavior of dark matter is essential for comprehending the overall process of galaxy evolution. Galaxies are also influenced by their environment. They can be found in various settings, from isolated regions to dense clusters containing hundreds or thousands of galaxies. The interactions between galaxies and their environments can lead to phenomena such as tidal stripping, where gravitational forces remove material from a galaxy, and ram pressure stripping, where the intergalactic medium strips gas from a galaxy as it moves through a cluster. These interactions can significantly impact a galaxy's ability to form new stars and can lead to the transformation of its morphology. The study of galaxy evolution also involves understanding the different types of galaxies. Galaxies are broadly classified into three main categories: spiral, elliptical, and irregular. Spiral galaxies, like the Milky Way, have a flat, rotating disk with spiral arms and a central bulge. Elliptical galaxies are more spherical or elongated and contain older stars with little new star formation. Irregular galaxies lack a distinct shape and often result from gravitational interactions or mergers. The transformation between these types, known as morphological evolution, is a key area of research in understanding how galaxies change over time. Moreover, The rate of star formation within a galaxy is a critical factor in its evolution. Galaxies with high rates of star formation are often referred to as starburst galaxies. These galaxies can form stars at rates hundreds of times greater than normal galaxies, often due to interactions or mergers. Conversely, some galaxies, known as quiescent galaxies, have little to no star formation activity. The transition from active star-forming galaxies to quiescent ones is an important aspect of galaxy evolution, influenced by factors such as the depletion of gas, feedback from supernovae, and the activity of supermassive black holes at the centers of galaxies. Supermassive black holes, which reside at the centers of most galaxies, including our own Milky Way, play a significant role in galaxy evolution. These black holes can influence their host galaxies through the release of energy and matter, a process known as active galactic nucleus feedback. This feedback can regulate star formation by heating or expelling gas, thereby affecting the growth and evolution of galaxies. As we explore the evolution of galaxies, we also consider the role of cosmic time. The universe has undergone significant changes over billions of years, and observing galaxies at different distances allows astronomers to look back in time and study the various stages of galaxy evolution. This observational approach, combined with theoretical models and simulations, provides a comprehensive understanding of how galaxies have evolved from the early universe to the present day. In summary, the evolution of galaxies is a complex interplay of processes involving gravity, dark matter, star formation, mergers, and environmental interactions. By studying these processes, astronomers gain insights into the history and future of galaxies, including our own Milky Way. As we continue to explore the universe, new discoveries and technologies will undoubtedly enhance our understanding of galaxy evolution, offering a deeper appreciation of the dynamic and ever-changing cosmos. What new revelations about galaxy evolution await us in the future? How will our understanding of these cosmic structures continue to evolve as we probe deeper into the universe's history? These questions drive the ongoing exploration and study of galaxy evolution, a field that remains at the forefront of astrophysical research. We explored the fascinating journey of cosmic structures as they grow and transform over billions of years. We delved into the processes that shape galaxies, from their initial formation to the complex, dynamic systems we observe today. We'd examine how galaxies interact with one another, merge, and sometimes even collide, leading to new formations and changes in structure. This act provided us with a deeper understanding of the life cycle of galaxies and the forces that drive their evolution across the vast expanse of the universe. We will explore a theoretical concept that addresses the ultimate fate of the universe. This concept is rooted in the laws of thermodynamics and cosmology, and it presents a scenario that is both intriguing and thought-provoking. What does the future hold for our universe? How do the principles of physics predict its eventual end? Let's dive into the concept of heat death and uncover what it means for the cosmos. The idea of heat death is tied to the second law of thermodynamics, which states that the total entropy or disorder of an isolated system will always increase over time. Entropy is a measure of the amount of energy in a system that is not available to do work. In simpler terms, it is a measure of disorder or randomness. As entropy increases, the energy available to do work decreases, leading to a state of equilibrium where no further energy transformations can occur. In the context of the universe, heat death refers to a state where all energy is evenly distributed, and there are no temperature differences to drive processes that require energy. This would mean that stars would burn out, galaxies would cease to form, and all matter would reach a uniform temperature. In this scenario, the universe would be in a state of maximum entropy, where no useful energy remains to sustain processes that we associate with life and activity. But how does the universe reach this state of heat death? It begins with the expansion of the universe, which has been occurring since the Big Bang. As the universe expands, galaxies move further apart, and the density of matter decreases. Over time, stars exhaust their nuclear fuel and cease to shine, leaving behind remnants such as white dwarfs, neutron stars, or black holes. Eventually, even these remnants will cool and fade away. The process of reaching heat death is incredibly slow, taking place over a timescale that is difficult for us to comprehend. We are talking about a future that is billions or even trillions of years away. During this time, the universe will continue to expand, and the energy density will continue to decrease. This expansion contributes to the increase in entropy, as energy becomes more and more spread out. One might wonder, is there any way to prevent or reverse this process? According to our current understanding of physics, the answer is no. The laws of thermodynamics dictate that entropy will continue to increase, and the universe will inevitably move towards a state of maximum entropy. This is a fundamental aspect of the universe's evolution, and it is a process that cannot be halted or reversed. However, it's important to note that the concept of heat death is a theoretical prediction based on our current understanding of physics. There are still many unknowns in cosmology, and new discoveries could potentially alter our understanding of the universe's fate. For instance, the nature of dark energy, which is driving the accelerated expansion of the universe, is not fully understood. Could it play a role in the ultimate fate of the universe? These are questions that scientists continue to explore. In addition to heat death, there are other theoretical scenarios for the end of the universe, such as the Big Crunch or the Big Rip. The Big Crunch suggests that the universe could eventually stop expanding and begin to contract, leading to a collapse back into a singularity. The Big Rip, on the other hand, proposes that the accelerated expansion of the universe could eventually tear apart galaxies, stars, and even atoms. Each of these scenarios presents a different vision of the universe's future, but heat death remains one of the most widely discussed possibilities. As we contemplate the concept of heat death, we are reminded of the vastness of time and the incredible scale of the universe. It challenges us to think about the nature of existence and the ultimate destiny of all that we know. While the idea of a universe devoid of energy and activity may seem bleak, it also highlights the beauty and complexity of the cosmos as it exists today. In conclusion, Act 30, Heat Death, invites us to explore the theoretical end of the universe as predicted by the laws of thermodynamics. It is a concept that underscores the inexorable march of entropy and the eventual fate of all cosmic structures. As we ponder this distant future, we are left with a deeper appreciation for the universe's current state and the mysteries that continue to unfold within it. What new discoveries await us in the field of cosmology? How will our understanding of the universe's fate evolve in the years to come? These are questions that continue to inspire and captivate scientists and curious minds alike.